Okay, welcome back everyone from lunch. It's my great pleasure to introduce our invited speaker, Dr. Kevin P. Hand. He's a planetary scientist and astrobiologist at NASA's Jet Propulsion Laboratory, where he directs the Ocean Worlds Lab. You can see a list of his accolades and accomplishments, including being the pre-project scientist for the Europa Lander mission and numerous things. The most recent exciting thing is his new book, Aliens, Oceans, The Search for Life in the Depths of Space. So I thought I'd read some peer reviews of his book for you. You very rarely get your peer reviews of a paper read out, but from director James Cameron, Kevin Peter Hand has delivered a beautiful portrayal of the science behind our search for life in alien oceans and the connection to our precious ocean here on Earth. A must-read for all who gaze at the stars above and ponder the abyss below. And from Robert Zubrin at the National Review, to paraphrase Hamlet, there are more things in heaven and earth than are dreamt of in our philosophy. Hand calls on us to probe the depths of alien oceans to discover them. I agree. So please give him a warm welcome for Dr. Hand as he guides us on this journey.
Thank you very much. I appreciate that, Cyrene, and thanks so much to the organizers for the invitation. Obviously, in 20 minutes, I'm not going to get through that much of all of the alien oceans in our solar system. And when Katie and team first asked me to come and speak, I was like, well, what is this crowd going to be interested in? And then as I started doing some more research, I was like, well, imaging and image processing. I'm going to use this as an opportunity to share a bunch of what I think are interesting videos of various experiments, and I'll finish with some field work that I think you might find interesting. And there's lots of ways in which the work that you're doing folds into both the lab, field, and mission work that I'll touch on. So to begin with, one of the most exciting and I would argue profound of discoveries that we have made in the past 60 plus years of solar system exploration is that we now know of oceans beyond Earth. Shown here is a portrait of the ocean worlds of our solar system. At the center, of course, is the ocean, is the Earth, with the ocean that we know and love and need to protect. And around the Earth, I've got Europa, Ganymede, and Callisto, 3 moons of Jupiter. These are moons that are covered in ice, and beneath their icy shells, we have good reason to believe that vast, global liquid water oceans exist. I've also got Titan and Enceladus, 2 moons of Saturn. These moons also are covered in ice. In the case of Titan, there's also a thick atmosphere, and beneath their icy shells, we've got good reason to predict that oceans exist. And I've even got Neptune's curious moon, Triton. These alien oceans of our outer solar system are really transforming our understanding of what it means for a world to be habitable. In the early days of astronomy and astrophysics, we had this kind of Goldilocks scenario. In order for a planet to be habitable, you had to have liquid water on the surface, and in order to be able to have liquid water on the surface, you needed to be at just the right distance from your parent star. In our case, of course, that's 1 astronomical unit, in order to maintain and sustain a liquid water ocean on the surface. If you were too close, like Venus, you boiled off any water. If you were too far away, like Mars, you froze out or lost any water. Now, the scenario with Venus, Earth, and Mars is much more complicated than what I've just described. But suffice to say, these moons of the outer solar system are teaching us that this is an old Goldilocks framework. There's a new Goldilocks for habitability, and it's one wherein the energy for maintaining and sustaining liquid water comes not from the energy of your parent star, but rather from the energy of tidal dissipation, that mechanical stretching that occurs as a moon like Io, shown here, goes around its giant primary, in this case, Jupiter. And Io, though it does not have an ocean, is the most volcanically active body in our solar system. To the north there, you can see an eruption of a volcano near the North Pole of Io. And Io is so volcanically active because of this tidal energy dissipation as Io goes around Jupiter on its slightly elliptical orbit. And in this kind of new Goldilocks framework, Io is sort of like Venus. Io lost any water that it once had. It's too energetic. And Callisto, well, we think it might have an ocean. It probably doesn't have much in the way of tidal energy dissipation. If it does have sort of a slushy layer, it's likely maintained through radiogenic decay of heavy elements. And so it's really Europa and Ganymede, and Europa in particular, that occupy this new sweet spot for habitability. We think that Europa has just the right amount of tidal energy dissipation so as to maintain a global liquid water ocean of about 100 kilometers or 60 miles in depth, and its ice shell is somewhere in the range of a few to perhaps as many as 20 kilometers in depth. Now on the long end that sounds quite thick, but we do think that Europa's ice shell provides a window into the chemistry and possible habitability of the ocean below. And of course, part of why these alien oceans are so compelling is because if we've learned anything from life on Earth, it's that where you find the liquid water, you almost always find life, whether it's life in extreme environments, like the places shown here, or life of extreme lifestyles. All life on Earth is based on liquid water. And I'd like to show this montage for another reason, which is that for all of the diversity of life on Earth, from the craziest of microbe to the craziest of rock star, all of life on Earth is connected by the same tree of life. We all run on DNA, RNA, proteins, ATP, etc. And just for reference, us, Mick Jagger, we are all just a tiny little twig down here in the eukaryotic branch. The rest is predominantly microbial life. And so when we think about these alien oceans beyond Earth, these are worlds that we can travel to with our robotic spacecraft and search for a second independent origin of life. We can search for independent trees of life. We can look and see whether or not there's some other way to get the business of life done. Is there another molecule like DNA that perhaps operates on these distant alien oceans? And this is an important contrast with our search for life on Mars. I do a lot of work on Mars, I love Mars, but on Mars there are two issues. One is that we're looking at old, ancient rocks, and in rocks that are billions of years old, which date back to the time when Mars was habitable and had oceans and seas, with rocks that are that old, you don't, DNA, large biomolecules don't last long. So when we get samples back from Mars, we're going to be looking for degraded organics. We won't be able to find any large biomolecules. And that means we won't be able to really reconstruct a tree of life from any evidence that is revealed of life on Mars. Coupled with that, Mars and the Earth are so close together that life on Earth might have seeded life on Mars or vice versa. And so even if we were to find life on Mars, if it did run on DNA, Occam's razor would sort of point to a cross-contamination between the two worlds. Whereas I would argue if we do find DNA-based life on some of these worlds, that would be an interesting example of biochemical contingency versus convergence. Maybe DNA is a convergent biomolecule. So these worlds really do represent an incredible opportunity to search for extant life, life that is alive today and whose biochemistry we could potentially understand. This is Europa. For the rest of my talk, I'm largely going to focus on Europa. It's sort of the canonical ocean world or alien ocean. It's about 3,000 kilometers in diameter. That means it's about the size of our moon, shown here to scale, both to our moon and the Earth. And all of those are shown to scale with Jupiter, which is some 318 times as massive as the Earth. I won't go through how we think we know Europa has an ocean. It's beautiful physics. In the interest of getting to some exciting experiments and videos, I'll simply make a shameless plug and say, read the book. And I go into a lot of detail on the various beautiful physics that gets into how we think we know an ocean exists there. But all of that folds together to an understanding of Europa where in cross-section we predict that it's got this ice shell, as I mentioned, that's a few to perhaps 20 kilometers in thickness, an ocean that's perhaps 100 kilometers in depth, and then an ocean floor, a sea floor, that's made of silicates and might have significant tidal dissipation so as to power hydrothermal vents. And on Earth, when we explore our own hydrothermal vents, we find incredibly diverse and intriguing ecosystems there that run on chemosynthesis, not on photosynthesis, the way our surface biosphere does. And Europa's ice shell, this is all water ice, it's fractured by that tidal tug and pull. And one of the things that I've explored in my lab is what exactly leads to this discoloration and the different hues that we see on Europa's surface. So for the next part of the talk, I want to dive into some of the experiments that we do in my lab at JPL. This is the Ocean World Lab, and we focus on two primary things. One is the chemistry, and in particular, the radiolytic chemistry of Europa's ice shell. Europa is bombarded by energetic electrons and ions due to the magnetosphere of Jupiter and the sourcing of ions from Jupiter's upper atmosphere and from volcanism on Io. And so not only do you have an icy surface at cryogenic temperatures without any atmosphere, you also have energetic electrons and ions bombarding that ice and other compounds and driving a very interesting radiolytic chemistry cycle. So one of the questions that had long been asked is, well, we think we have evidence from the magnetometer data on Galileo that Europa has a salty ocean. Well, certainly if it's got a salty ocean, we should see some salts on the surface. But it turns out that the spectra from the Galileo mission, which flew by Europa in the late 90s and early 2000s, those spectra were not at high enough resolution to put the nail on the coffin of yes, this is salt on the surface. To get at this in the past decade or so, I've done a number of experiments in this simulation chamber where we can get down to the temperature, pressure, and turn on the electron gun to get at the radiation environment. And what I've done is put in alkali halide salt. So here's sodium chloride. You all know and love sodium chloride, table salts. It's spectrally flat and appears white to the eye. But after irradiation, and this is some video, this is me hacking together some video inside the chamber with my DSLR. And what you're looking at is a rastering of the electron gun over an evaporite of salt under Europa conditions. And it turns out that alkali halide salts have this beautiful property of capturing electrons. And when they do that, they become essentially a simple harmonic oscillator. The electrons do in the vacancies within the alkali halide crystal structure. And what that leads to is that salt, instead of appearing flat white, takes on a color, this beautiful kind of yellow, brown, in some case sort of a reddish color. And working with my colleague Mike Brown and graduate student Samantha Trumbo at the time, we ended up getting some Hubble time to look at Europa, and we were actually able to match my laboratory spectra, shown in red, to the Hubble spectra, shown in black there, where that specific absorption due to the irradiated sodium chloride matched the Hubble data beautifully for that particular region on Europa. And we think this is the best evidence to date of Europa's salty ice shell being indicative of a salty ocean below. Now, the Galileo mission was phenomenal, but the high gain antenna on it did not work. And as a result, we were left with very few high resolution images. This is one mosaic showing Europa's surface at about 6 to 10 meters per pixel. This is a grayscale image. If this was in color, much of the black and gray you see here would likely be reddish brown or yellow, indicative of salts, maybe organics, maybe some European krill, who knows. But the cliffs that you see here are about 100 meters in height in the case of that cliff that just passed by. And we really don't know what Europa's surface looks like at the meter scale. And one of the big projects that I focus on is trying to land on Europa. And there's been a lot of debate about, well, on Earth, when we go to places like the ice fields of Kilimanjaro, this was an expedition I was on a number of years ago, when you go to high altitude equatorial environments on Earth, you see these structures, things like massive sun cups, and in this case, penitentes, these structures at the meter scale that could harm or pose a real challenge to a lander that you're trying to set down on the surface. So one of the other things we do in my lab is trying to understand the evolution of surface snow and ice morphologies. And what I'd like to share with you next are some results of some experiments that we've done in a very large chamber that we call the Ark. We call it the Ark because it looks like the Ark from the Raiders of the Lost Ark movie. You can see the little movie poster on the front there. So we can put snow or ice in this. This is a time-lapse video showing water freezing inside the chamber. Those bubble towers that you saw, that was essentially a slow boil. Now you're seeing that water freeze. You can see some pressure ridges forming. And this was just kind of the initial setup before passing the LED bar. And I should, this might be a little dizzying to you. This experiment we ran for many months at initially 130K, and then we ramped up. And what we're doing here, this LED bar simulates solar irradiance. So this is the amount of sunlight across the spectrum that ice would experience at Europa. And we're trying to just understand the evolution of this icy surface. I'm going to skip forward a little bit here, and what you'll see is that gradually we did not form any ice spikes, but instead we formed this beautiful, almost like, here it looks like a marshmallow structure. It's called a botryoidal structure, somewhat akin to malachite, if you know that mineral. Here's just a nice image showing the final formation. No one had ever seen this before, and so we're working to analyze many of these features, almost like tree rings, but instead of in trees, we're looking at the various rings in the ice. Now, what that experiment showed is that we did not grow ice spikes, but we actually have done a few other experiments with porous snow. And here again, you can see a time lapse. I'll skip forward a bit here. And what's happening in the evolution of this ice is that it's all sublimation-driven erosion. On Earth, the reason we get some of these structures is because you've got the diffusion equation where the atmosphere is interacting with your icy surface. And as a result, those water molecules that are coming off of the snow and ice have an atmosphere that kind of modulates the snow surface. On Europa, there's no atmosphere, and so the mean free path of a water molecule is of order many, many kilometers. And so the snow just erodes away quite efficiently. To actually get at this issue of penitentes, we seeded the chamber with a cake that was corrugated, and we wanted to see what this cake looked like over time. So this is kind of we had 6 different cameras. I'll just share with you this one view, and you can see as we gradually increase the temperature to increase the sublimation rate, the troughs of the penitentes stayed the same, but the peaks eroded away. And in that article that I showed earlier, we get into some of the physics of why you get this preferential erosion at the peaks and the valleys stay stable. We ran this experiment for as long as we could. These experiments are largely limited by the stability of the building at JPL in which my lab is hosted. So we run these for weeks to months, and sometimes there's power outages in the buildings, and those end up being the limiting factor. So I'll finish with just a bit about what's next in terms of missions, and close with a bit on the field work. NASA has committed to the Europa Clipper mission. This will launch in 2024 and get out to Jupiter and Europa in the 2030 timeframe. ESA, the European Space Agency, has also committed to the Jupiter Icy Moons Explorer mission, and this will get out to Jupiter in the same time frame. It will fly by Europa, and then it will go into orbit around Ganymede. Following on that, my dream has been to land on the surface of Europa to actually search for signs of life. And we've spent about $300 million invested in this mission. Unfortunately, the most recent decadal survey that came out did not prioritize landing on Europa. And so unless we figure out some other way to get this done, we're not likely to land on Europa until the year 2050 at the earliest. I do have some other hopes for getting it done. But just recently, I returned from a field test where we deployed a prototype of the Europa Lander, and the engineering team up there was specifically looking into autonomous sampling of icy surfaces. This is a drone footage captured by my friend and colleague Roland Brockers, and this is a glacier up in Alaska, the Matanuska Glacier. I just returned on Sunday, and we're going to pan up. You'll see our field site there, and you'll see the Europa Lander situated in a Europa-like environment. We're going to fly by the lander, and as we do, you'll see the arm with this ice pick tool that can drill into the surface. And what's amazing here is that the autonomy on this system utilizes imagery, LiDAR, a number of sensors in the actuators so nobody's joysticking this. When we land on Europa, the time difference, the urgency to get things done, we're going to want to have that lander have a significant amount of intelligence and autonomy so it can get started with our science right away. And so these engineers, within a few hours of getting the lander set up, this robotic arm was doing autonomous sampling in this very hard glacial ice. It looks like snow, but it's actually very hard ice. And the team is up there for about another week and a half, going to a few different sites. Really remarkable effort. This is the most sort of Europa-like environment that this prototype has been tested in, and a lot of credit to the team for getting this done. So here's just an up close of the vehicle. There's a little bit of motor noise that you might be able to hear there, but that gives you a little closer look at it, digging a trench to get a subsurface sample. So thank you very much for the invite, and really appreciate your time and hope you enjoyed learning a bit about alien oceans.
So we have time for 1 or 2 questions.
So does Europa have a magnetic field? And if so, why is it not important to model it in the arc?
Thank you very much. So Europa does not have its own intrinsic magnetic field. In fact, some of the best evidence for Europa's subsurface ocean comes from detection of an induced magnetic field at Europa by the Galileo mission. And that induced magnetic field is created by Jupiter's time-varying magnetic field. And so as Jupiter's field sweeps by Europa, the salty ocean serves as the conductor in which electric currents are excited, and then an induced magnetic field can arise. And so on the Clipper mission, there's a magnetometer that will, during each of the flybys, will measure that magnetic field and give us new insights into the extent of the ocean itself. In the arc, it's all ice, and so there's no liquid water. We have done some experiments on the conductivity of salty ice and sulfuric acid ice, but compared to liquid water, the conductivity of those ices is significantly reduced.
I see. Thank you. Really nice talk.
Thank you very much.
Okay. Does the salt that you found in the ocean have any bearing on life, or is it just another fact about the ocean?
Yeah, so first and foremost, the thing that the salt tells me is that this ocean is cycling with a geologically active seafloor. And this actually gets at the heart of a debate that I'll try to summarize in 30 seconds. Prior to our work that I showed here with sodium chloride, there was one camp of scientists that said, oh, that reddish material that we see is magnesium sulfate salt derived from the ocean. And the problem that I always had with magnesium sulfate, aside from the fact that it didn't match the spectra particularly well, is that magnesium sulfate does not have a long residence time in an active ocean. Our ocean here on Earth has very little magnesium sulfate because as the water goes through our lithosphere, our oceanic crust, the magnesium and sulfur gets drawn down into the rocks in the crust. What does have a long residence time is sodium chloride. That's why our ocean is full of NaCl. And so the fact that we've found sodium chloride on the surface of Europa tells me that this ocean is cycling through an active rocky seafloor, which from a habitability standpoint might indicate hydrothermal vents and a lot of chemistry that life could use.
One last question.
Thanks for this very interesting talk. I guess the question I may have is, I think you touched on at the end about potentially sensors for the exploratory vehicle, but in general, do you have maybe like a call to action for what sort of challenges on the computational imaging side, computer graphics, computer vision that interest you most? What sort of solutions interest you most for the problems you face?
Yeah, it's a great question, and I'll have a much better answer to your question once the field team comes back. And part of the reason that we did this field campaign is to test out our sensors there and see how they do with the specular reflectance of snow and ice. As you can imagine, this is a very high dynamic range environment. On this particular day, it was very sunny, and so some of the things that we are looking at and exploring is, and this will be true on Europa, where there's no diffuse scattering from the atmosphere, you're dealing with a shadow that's going to be pitch black, and then if sunlight is shining on the ice, now you're dealing with a very bright surface, and you're relying on your imagery and doing the image processing to select a sampling site, and you're also trying to look down into that trench and potentially both from band passes in the camera and possibly from a spectrometer on the mast there, figure out if there's any organics or other materials in the ice. So that sort of changing environment due to sublimation, and in this case melting, and the high dynamic range environment, and just the difference in spectral properties of ice relative to things that we have a lot of experience with, like rocks on the moon and rocks on Mars. That's going to be what I'll be passing forward to a field like yours.
Yeah, this, if you may indulge me a quick comment on that, I think that,
I think we're going to press for time. Sorry, we would love to talk about alien oceans for the rest of the afternoon, but you can also read the book and talk to him offline. So let's thank Dr. Hand again for this.
Thank you. Yeah, and please follow up, and we're always looking for bright students, and thank you so much for your time. Let's see what's... That's mine. Yeah.
Hi everyone, my name is Mary Jen and I'm a graduate student at Rice University, and I have the honor to introduce the next group of speakers. And first we have Bhavya Goyal from the University of Wisconsin-Madison, and he will be presenting on robust scene inference under noise blur dual corruptions.
Hi everyone, I'm Bhavya. I'm a PhD student at University of Wisconsin-Madison, and I'm advised by Professor Mohit Gupta. Today I'll talk about our work which is titled Robust Scene Inference under Noise, Blur, Dual Corruptions, where we tackle this problem of doing scene inference under very low light and motion conditions. This is a joint work with Professor Jean-Francois at University of Laval and Professor Yeung at University of Wisconsin-Madison. So generally, computer vision models are trained and tested on images captured under sufficient light. But under low light conditions, the captured images are very dark, and when we do inference tasks like image classification or object detection, those becomes very challenging. And the reason for that is there's a lot of noise in low light images. As you can see from this image on the left, which is captured under extremely low light condition, and this image on the right, which is the scaled up version of the first image, you can see that there is a lot of noise in the image, which is why this image has very low SNR, and inference becomes challenging because of this. One way to increase this SNR in this image is to capture longer exposure images. When we capture longer exposure images, we get high SNR images, which helps us in doing better inference. But when there's the condition of scene motion or camera motion, and we try to capture long exposure images, we tend to get a lot of blur, which again also reduces the performance of our models, inference models. So now that we've seen that there's both noise and blur image degradations at play, we can look at this example of simulated images in low light and motion condition. So in this example, we have increasing exposure images from left to right. And you can notice that as we go towards the right, the noise tends to decrease, but the blur in the captured images is increasing. So we can make an observation here that there is this trade-off between noise and blur image degradation, because if we decrease one, we tend to increase the other. So we call this noise-blur dual. And so the question that you might ask is, if all of these captures in this continuous spectrum of noise-blur dual, if they're all corrupted with noise-blur dual corruption, which exposure is most suitable for recognition? Well, we can look at this example where we capture this scene in very low light, and it contains a stationary object, a chair, and a moving person. And you can see that this short exposure image is very noisy, and it detects false positives. But as we increase the exposure and we go towards the right image, we see that the noise tends to decrease, but the blur increases, which makes it difficult for the fast-moving objects to be detected. So you can see that the person is not detected in the image on the right. So this tells us that all of these exposures, they suffer from this noise blur corruption, and none of them are fully capable of doing inference on their own. But one interesting observation we can make here is that all of these exposures, they make different errors. The short exposure images tend to work well on fast-moving objects, and long exposure images tend to work well on stationary objects. So we can almost say that different exposures, they have complementary information that can help us in inference. So the question that comes to mind is, can we somehow get all of these exposures and then try to do inference? The answer to that is yes, we can. So we have these cameras coming up which allows us to code different exposures, spatially varying exposure for different pixels, almost like a Bayer pattern. For example, short, medium, long exposure in a grid form. We saw similar work in Monday's talk earlier using SCAMP cameras. So which gives us a coded image with different exposures, and which can then be interpolated to get multiple exposures. There's another simple way to get this. Just use any modern smartphone cameras. Most of our cameras have HDR capabilities. They already do exposure bracketing to get these multiple exposures, and we can use that for inference too. So now that we know we can capture these exposures, what we propose is leveraging all of these exposure to do better inference. And our key idea is get individual predictions from all of these multiple exposures of varying exposure, and then do ensemble and use the ensemble prediction as your final output. And because all of them have complementary information for inference, we will hope to get better inference because of this ensemble. And another thing that we can leverage here is that all of these exposures, they have been taken from the same scene. So even though they have different amounts of noise and blur, but the semantic content in all of them is same. So if an image contains a cat or a person in the same spot, all of those different variations of the same image will have the same semantic content. So what we propose is to use some semantic consistency across multiple exposures by enforcing some kind of a consistency loss on the output features of these images so that they all are closer in the output feature space. So let's look at how we can use both of these techniques in a conventional inference pipeline. So usually we have like a image and which we use through a feature extractor, like a CNN, ResNet kind of an architecture. And then we have a prediction module which gives us a label for the image, like a cat or a dog, similar to an image classification task. What we propose is we will use multiple exposures for training too. We will extract features from all of these exposures, and we would introduce this feature consistency loss, which would push the output features from all of these exposures closer to each other and closer to the clean image, which contains hopefully more better quality features. And then we'll get output from all the individual exposures during test time. We would use the ensemble prediction from multiple exposures as our final output. So that's pretty much the way that you can use it for any computer vision task like image classification, object detection, and so on. So we evaluated our approach on a few different tasks on simulated data sets and real data sets. So I'll show you a few examples of the simulated data set first. This is how we generated our simulated data set. We used high-speed videos, and we simulated low-light frames from low-light images from each frame, and averaged different number of consecutive frames to get longer exposure captures. So here's an example at the bottom of our simulated frames that we use from this video. And we created 3 different benchmarks to evaluate our object detection models. So the one at the top is the REDS data set, which contains urban scenes and urban environment conditions. Second data set is the cityscapes data set, which contains driving scenarios and contains lots of cars and pedestrians and similar classes. And the third one is the MS-COCO data set, which is web-crawled images and contains general categories of objects. I'll show a few results on those simulated images. So if you can see, these 2 images are short and long exposure images from the data set that I just described. And when we do inference using a conventional computer vision model, we see short exposure images have false positives. Long exposure images, as you can see, fail to perform well on moving objects like this bus on the right. And you can compare it with the ground truth that both of them, none of them are able to get all 3 buses, bounding box for all 3 buses correctly. But our approach, which is trained with semantic consistency, and it uses multiple exposure ensemble, it performs significantly better on both stationary and moving objects. Similarly, there's another example with 4 different exposures Since our approach is versatile to a number of exposures that we can use, in this case, we show an example with 4 different exposures. All of these exposures have either false positives or missing bounding boxes. False ones are highlighted in red, green ones are the correct ones. And our approach, as you can see on the bottom left, performs reasonably better than all of those. We also evaluate our approach on real captures. We mimic this multiple exposure capture by using multiple cameras. We stack 4 different cameras together to get the same field of view. And then we trigger simultaneous capture with different exposures on each cameras. We do this on a bunch of different settings. Some indoor settings where we control the lighting to be very low, and some outdoor settings where we put these cameras on a car and we drive at night. So it simulates low light and motion conditions like a regular driving at night environment. So here is an example with the indoor setting, which I also briefly discussed earlier. You can see that there are false positives in the short exposure. The moving person here suffers from the blur, and there's a missing bounding box for that. But multiple exposure ensemble works much better than the individual ones. Similarly, here's the second example where we put this on a car. And as you can imagine, in a driving setting, the peripheral objects like this car has a lot of blur, and long exposures usually tend to fail on these kinds of scenarios, and short exposures fail on like this traffic light and other stationary noisy objects. And multiple exposure ensemble works well on all kinds of objects, both stationary and moving. So in summary, we explored this noise blur dual space, which comes into play when we have low light and motion conditions. And we propose to use this semantic consistency, which helps us to learn robust models to do inference. And we use this multi-exposure ensemble approach to get complementary information from a variety of exposures so that we can get more robust inference. We have more results on a variety of tasks in our paper, so feel free to look into more details for the experiments. That's it. Thanks.
We have time for 1 to 2 questions.
Thank you. Nice talk. One of the ways to make to resolve the noise problem without having to increase the exposure is to use a lens that has a huge aperture, right? But that results in defocus blur. Wouldn't it be possible to still do that and enforce your semantic consistency and get results from both really high quality SNR images, but corrupted by defocus blur?
That's a good question. I think I'm not sure if there exists a dual between low light noise and defocus blur, but I would say that this semantic consistency approach tries to push any kind of degraded images close to clean images and closer to each other. So as long as there is semantic consistency between different exposures and different captures, it should benefit from it. So yeah, I would hope that it also works, but yeah, I would also be interested to see that.
All right, thanks.
Hi, yeah, nice talk. Really cool work. I was wondering, did you also look into sort of the opposite end of sort of this ensemble method, which would be to just fuse the brackets pre-optimizing for motion freezing SNR and sort of comparing those results? Like, was that investigated, or?
Yeah, thanks for the question. I think that's a good question. So I think there are already a lot of approaches which do that. If you think about like HDR imaging and so on, they do exposure bracketing and then try to reconstruct the image first. But I think our focus is not necessarily on getting images of higher quality. When we get a lot of motion in the scene, those approaches tend to fail. So that's why we went with this approach, because even though the image reconstruction fails, inference should work really well. So that's kind of the main intuition.
I see. So you think this would still be a better method than, for example, a high-quality image fusion HDR algorithm?
Yeah, I definitely believe so. And in our paper, we show results with some image reconstructions like denoising, deblurring, and so on.
I see. Okay.
But that will also be interesting to see with how it performs with HDR.
Yeah, my second question was, and it sounds like you investigated also sort of just denoising the short exposure.
Right.
Okay.
Yeah, I may have some results. Like in the paper, we show some results with like denoising, deblurring, denoising and deblurring, and so on. So I definitely encourage you to look into more details of some reconstruction approaches and some more quantitative results too.
Awesome. Thanks. Cool.
Thank you.
Okay, let's thank Bhavya again for his presentation. Next, we have Yingshu Chen from the Hong Kong University of Science and Technology presenting on time-of-day neural style transfer for architectural photographs.
Yeah, good afternoon, everyone. I'm Yingshu Chen from the Hong Kong University of Science and Technology. Today, I would like to introduce our work, the time-of-day neural style transfer for the architectural photos, which is actually the photorealistic style transfer for the outdoor architectural photos, achieving time-lapse effect in a neural image-to-image translation manner. We know the style transfer has been a long-standing problem for image processing or image translation. Giving a source image and style reference, some deep learning-based approach like neural style transfer or image-to-image translation approaches, they achieve artistic style transfer or some domain image translation works at really fast inference time. However, if we want to transfer the style for the architectural photo, which has a very special structure, the architectural photo has the dynamic texture of the background in the sky, such as the dynamic cloud shapes or texture and different color during the day. But for the foreground, there's always some static objects. So if we would like to transfer the style for such a architectural photos, we need to transfer the different new texture and shape for the clouds in the background, while we can only transfer the sufficient color styles for the foreground, and we need to preserve the foreground geometry intact. So far, the already existing general neural style transfer or image-to-image translation works, they treat the image as a whole entity, and without knowing which part is the foreground and background. So therefore, they may lead to some geometry distortion for the building in the foreground or lead to some mismatched color transfer. In our work, we propose such a new problem setting for the architectural style transfer of different times in a day. Given an architectural photo and a style reference, we aim to transfer a novel sky texture and color for the background. And we need to transfer a new foreground style sufficiently with intact geometry. To achieve separate style transfer for the outdoor scene, we propose such a new framework for architectural style transfer, mainly including 3 steps: the image segmentation, image translation, and finally we have a blending optimization, which can help us to output the original high resolution in high fidelity output. The first step, we need to segment the foreground and background, which actually is a very easy task because we already have a lot of pre-trained model which can efficiently segment the sky background. And what we need to do is just segment the sky as background and keep the remaining as the foreground. So during our training, we just directly use a pre-trained model for the segmentation because we found the model is tolerant for imperfect segmentation. But of course, you can manually label the segments. With the separate foreground and background information, now we can train two different image translation models for foreground style transfer and background style transfer separately. And then we can achieve more semantic style transfer. In the image translation part, inspired by a lot of previous model image to image translation works, which can achieve exemplar-based style transfer. We use the bidirectional image to image translation network architecture. And we also apply the content and style reconstruction loss, cycle consistent loss, and the GAN adversarial losses. However, if we directly train such a network, such an image-to-image translation network, they usually still fail to preserve the perfect geometry and would destroy the architecture texture or generate some new texture for the whole image. Therefore, we need to particularly handle this case. Because we need to transfer only the color for the foreground. So we have an assumption that we assume the luminance of the image should contain sufficient geometry information and the illumination information. And then we define such a geometry losses containing the image gradient loss. And at the same time, we would like to constrain the foreground luminance distribution. For example, here, we would like to transfer a daytime image to a nighttime image. The foreground illumination distribution from a brighter distribution to a darker one. And from our result, we found such a combination of these two losses. Such a geometry losses can have a better geometry preservation than a lot of previous image-to-image translation works. Because we trained the network in relatively low resolution, like 256 or 512, but actually in the real world practice use, for example, we casually capture a auto scene photo. Usually they are really in high resolution. Therefore, we apply such a post-processing step, a blending optimization for the low resolution blended output, which can restore the original high-resolution source image geometry perfectly. And at the same time, we can still preserve the translated style. We directly use similar technique in the PGGAN, which they train a model to predict the style constraint for the blended image. Instead, we can directly use the low-resolution blended output from the image translation network as the color and constraint, And giving the high-resolution source input, we can use that as the high-frequency geometry information constraint. Finally, we can output the high-resolution new translated image. So no matter how high the resolution of your source image, we can always output the same high resolution output. Even now we have a good performance framework for architectural style transfer, we still need a really good data set for such a task. We found there were no such a good-looking like time-lapse video or image data set. Therefore, we have to collect the new unpaired data set from the internet. At the same time, we also extract some frames from some good-looking time-lapse video. So finally, we collected around 20,000 architectural photos for training and 1,000 photos for evaluation. At the same time, we have a new definition of the time of day styles. We manually label 4 different classes: the daytime, golden hour, blue hour, and the nighttime styles. And this data set can be a new benchmark for the architectural style transfer. With the collected data set, now we can conduct an experiment to validate our approach. So our strategy to separately transfer the foreground and background style can achieve a better thematic style. Our proposed geometry losses can largely preserve the geometry detail, and the blending optimization can further restore the high-frequency geometry information and enhance the photorealism. We also compare to a lot of state-of-the-art image-to-image translation and general neural style transfer approaches. From the results, our work can always achieve a better photorealistic style transfer. We can transfer more semantically matched style and while preserving the correct structure. Let's compare more visual results to some image-to-image translation works. Given the same scene, I will show 3 different style transfer results. M-Unit is a very typical multimodal image-to-image translation work. It can somehow preserve, to some extent, some geometry, but it still failed to correctly transfer the thematic color. For example, here, it would like to transfer the background color to the foreground and also have some texture artifacts in the building facade. This more latest work even destroyed the original geometry of the building, and as well, there are a lot of wrong color transfer. And our work can perfectly transfer correct color and style for foreground and background separately, and the optimized version can even improve greatly the geometry information, especially for the building details. Let's check out the comparison for the neural style transfer. This very typical popular artistic style transfer work, we try to weigh up the content loss during training, but however, we found out it will always tend to transfer the texture, no matter for the background and foreground, and achieving very artistic results. And this latest style transfer work, it considered both the local and global style statistic transfer, but it still generate very artistic results with brand new texture. Our work can always transfer more photorealistic style transfer, and the optimized version, again, can preserve and improve more geometry detail in really high resolution. So here I show more different styles for the same scene transfer translation, the golden hour, blue hour, and nighttime new style. So to summarize, we have a new style transfer task, the photorealistic style transfer for the architectural photos of different times in a day. And we also propose a new image-to-image translation framework with separate style transfer for the foreground and background, with the geometry losses, which can preserve the image content. And our new collected data set of the architectural photos can set up a new extensive benchmark for such an architectural style transfer. So if you're interested in our work, you can refer to our paper or visit our webpage. There will be more different examples and results, and we will also release the code and data. Yeah, thank you.
Time for questions? Okay, well, I guess I'm exercising my right as the session chair. I'm wondering if, given the right data set, can this method also be applied to portraits?
Yeah, actually, yesterday in the process section, a lot of people asked me similar questions. Actually, I mean, the key idea for this architectural photo style transfer, because it has a special structure for the scene, the dynamic portion, and static portion. Of course, for portrait scene, I would say scene, we have, if we want to change the background and keep the portrait, the geometry and shape, of course, we can using a similar technique. And it would be very interesting if, imagine if we have a group photo and then we direct change the background. And of course, data set might be a very necessary using this technique now. But of course, we in the future, maybe we can improve the technique and may not need to like data-hungry technique.
Okay, let's thank Yingshu again for her presentation. Next, we have two virtual presentations.
We present MPS-NeRF, a new method for generalizable 3D human rendering from multiview images. Freeview human character rendering and animation has numerous applications, such as virtual reality human, telepresence, among others. While traditional methods usually use dense multiview camera rigs or depth sensors to accomplish this task, which have high capture cost. Recent neural rendering approaches have shown that freeview rendering and animation can be achieved using only sparse color cameras, which could significantly reduce the device setup and capture cost. Some methods combine 3D point cloud feature and scene renderer to generate rendering results. However, their rendering quality is sensitive to the point cloud density and cannot guarantee 3D view consistency. Recently, promising results have been shown by NeuroBody, which are based on the NeRF and SMPR model. With NeRF, the generated multiview images not only have decent quality, but also enjoy high 3D consistency. However, existing NeRF-based methods are typically trained in a person-specific setup, which means one model is trained for one single person. Such a setup is clearly not scalable, as rendering any new character would require a tedious model training process. Moreover, they need multiview video for training in order to handle different human poses, which restricts the practical usefulness. Therefore, we propose a novel, challenging, but more practical task, training a model that can render on-scene persons in a feed-forward manner, and using only still images to capture the sparse viewpoint as input. The generated 3D human model can also be animated to any normal pose. A simple yet effective method is also proposed for this task. We introduced MPS-NeRF, a new method for generalizable 3D human rendering from multiview images. One of our key insights is that human bodies share a similar geometric structure, which can be leveraged to learn a generic rendering model. Besides, prior studies such as IBR-Night have shown that using images as conditional input, it is possible to train generic NeRF for common objects. Although these methods focus on rigid objects or static scenes, the spirit of generalization applies to our problem as well. Next, I will briefly introduce our method. Firstly, to render the target image, we cast the array to the 3D space within sample points along the array, predict their density and colors using a neural network. The key lies in how we compute the density and color for a point in the target space. A straightforward solution would be projecting xt onto the image planes to get features, and then combining them with xt as the input to NeRF. However, the complex, non-rigid human motions make the reading field prediction difficult to learn and generalize to different people with various poses. Besides, these methods can only be applied to the novel view synthesis task. For novel pose synthesis, it lacks a way to handle pose change for feature retrieval, nor does it offer a mechanism to drive an animation with desired pose change. To attain better generalization capability and generate novel pose images, we learn a reading field in a canonical space, where different people with various poses are well aligned based on the SMPL model. To predict the density and color, we deform xt to this canonical space and use the deformed point as the input to the network instead of xt. The point is further deformed to the observation space and projected onto the input images to retrieve multiview features. We formulate our deformation as an extended scaling process by propagating the surface scaling width of SMPR model to the volume. The SMPR model provides a predefined scaling width factor for each vertex on the body surface for scaling. For each point in the volume, we assign the scaling width of its closest body vertex. With assigned scaling width, volume deformation can be calculated by the LBS algorithm and inverse LBS, respectively. The deformations so obtained provide an approximation of the true correspondence field when the target and observation poses are different. Although the deformation so obtained is simple and cannot perfectly model all complex motions, our rendering scheme is volumetric rendering, and is learned to achieve best image rendering quality to the extent possible. For canonical space point xc, we deform it to the observation space. A set of features is extracted using bilinear interpolation after projection. Next, we fuse the extracted multiview features for subsequent radiant field prediction. Human images usually contain severe self-occlusions. Thus, feature fusion is not trivial, especially on the very few views. In our method, we employ the attention mechanism in transformers for effective feature fusion. We emphasize that our method is different from previous attention-based NeRF methods in that we propose to use two attention MLP to generate two features for color and geometry respectively. Generating two features should not only increase the representation power, but also ease the feature fusion learning process. The fused feature, together with the coordinate of canonical space point, are fed into an MLP network to predict color and density. Finally, we can do volumetric rendering procedure for array in the target space. To further regularize the geometry, we add a constraint that the learned geometry shouldn't be too far away from the fitted simple model. Specifically, we penalize the norm of xc in our learned geometry and that of the nearest body vertex y normal on the simple body surface. We also incorporate a normal smoothness prior to encourage smooth geometry. Next, I will show some visual results on human 3.6M dataset. Here, bottom left is normal view synthesis results, bottom right is normal pose synthesis results. We need to note that the input is only a sparse set of multiview images of an unseen person during training. We also show a comparison results with animatable NeRF and neural body. They are trained on this single person using multiview and multi-frame data. We can see that our method shows a comparable performance of neural body, and even better than animatable NeRF. Next, I will show some visual results on T-human dataset. Here, bottom left is the normal view synthesis results, bottom right is the normal pose synthesis results. We need to note that the input is only a sparse set of multiview images of an unseen person during training. We also show a comparison results. Here, animatable NeRF clearly underperform in this case, as the pose number for each person is limited and there is no global body rotation. So it struggles to predict a reasonable residual scaling field during normal pose synthesis. Visually inspected, neural body and our method are able to generate reasonable results with a comparable quality. We present the quantitative comparison of our MPS-NeRF with the other two methods. Although the testing person are unseen to MPS-NeRF, it yields better normal view synthesis results and comparable normal pose synthesis results on H36M dataset. Besides, our method outperforms in both normal view and normal pose synthesis on T-human dataset. Although NeRF-based methods doesn't explicitly recover 3D geometry, we can still extract 3D shapes using the density field. This figure presents the extracted 3D shape for the input images, as well as the reposed target shapes using our deformation scheme. Note that we didn't apply any post-processing on the extracted 3D shapes, such as the Gaussian smoothing, which is used in animatable NeRF. To validate the importance of using a canonical space, We remove it in our implementation and retrain our model. As can be observed, the results without the canonical space contain more unwanted artifacts. Moreover, the predicted human boundary is clearly erroneous. We also verify the efficacy of our attention-based feature fusion scheme by replacing it with a simple feature average pooling strategy. This figure shows that without our attention-based fusion, the synthesis images are blurry and suffer from severe color distortions. We also show the ablation results on our loss terms. The shape loss imposes stronger regularization on geometry, without which obvious geometry distortion may occur. The smoothness loss also improves the geometry by diminishing the noisy and disconnected regions. The improved geometry leads to better rendering quality. Thanks for your attention.
We have time for questions. Xiangjun, can you hear us?
Yeah, I can hear you.
Okay, we have time for questions. Anyone have questions? Okay, I guess I can ask a question. So how many views and poses are used to get, during test time, to generate new pose and new views? And does the performance increase with the increase, if you input more views or poses?
Yeah, good question. Actually, we use 3 viewers inputs during the test, and we also try to increase the view number of input, and with the view number increase, the performance of our model also increased.
Okay, thank you. Do we have any questions from the audience? Okay. Thank you so much. Let's thank Xiangjun again for his presentation.
Okay, thank you.
Next, we have Hongju Ku from KAIST presenting on differentiable appearance acquisition from a flash-no-flash RGBD pair.
Hi, I'm Hyunjin Gu from KAIST. I'll present differentiable appearance acquisition from a flash-no-flash RGBD pair. This work is a collaborative work with Hyunwoo Ha, Joo-ho Lee, Da-hyung Kang, James Tomkin, and Min-H Kim. Rendering is a process to generate 2D images from 3D models. It requires 3D geometry, reflectance map, lighting conditions, camera parameters. Inverse rendering is the opposite procedure. Given 2D images, obtain information needed for rendering. Appearance acquisition is needed in this step to contain reflectance information. Through inverse rendering, we can reconstruct objects in real world, and we can play with the objects with realistic appearance. There are previous works that try to reconstruct intrinsic properties of objects from a few shots of RGBD images. Baron et al. And Kao et al. Take this approach. They estimate intrinsic property of objects successfully, but reflectance is limited to diffuse albedo only. There are also deep learning-based approaches. Sang et al. And Bose et al. Use thousands of rendered images, including geometry and reflectance, to train deep learning network to obtain SVBRDF. These approaches are fast, but the model is easily overfitted to the trained data, which makes it hard to adapt to various real-world objects. For input, we use an RGB image pair with and without a flashlight and a depth map. Our method estimates diffuse albedo, specular albedo, surface roughness, and refined normal and depths. These input images can be obtained with a DSLR camera and a depth sensor, or just with a conventional mobile phone. Now, I'll give you an overview of our method. First, from the coarse depth map, we compute initial normals. From flash and no flash image, we compute flash-only image while assuming flashlight as a point light source. And from no flash image, we cluster colors for material segments. The optimization is done in two steps. First, we estimate environment illumination, assuming no flash image is taken under diffuse ambient light. Then, under this illumination, we jointly optimize SVBRDF and geometry-related parameters. We first obtain a flash-only image by subtracting the ambient-only image from the flashlight image. We mainly use flash-only image for the joint optimization, since we assume that there's only one point light source. We can simply formulate the flash-only image as the multiplication of shading and BRDF. Here, we use the Cook-Torrance model for BRDF, which is summation of diffuse and specular reflection terms. Let's look at the detail of the optimization part. In step 1, we estimate environment illumination in order to obtain diffuse albedo Q from no flash image. By assuming no flash image is taken under diffuse illumination, we can parameterize the illumination G as 9 coefficients of the second order spherical harmonic spaces function. Once G is optimized, we can compute diffuse albedo as well. Later, this diffuse albedo is used to register the diffuse albedo obtained from flash-only image. In step 2, the joint optimization is done in coarse-to-fine manner, and there are 5 optimization parameters being used. To obtain refined geometry, we use depth difference matrix and relative rotation matrix. To obtain SVBRDF, we use per pixel diffuse albedo and specular albedo and roughness per material cluster. Let's look at the objective function more detail. Our objective function consists of 3 photometric terms and 3 geometric terms. The first term is photometric consistency term. This term reduces the difference between input flash-only image and rendered image in foreground pixels. Second term is diffuse albedo constraint. This constraint reduces difference between optimization target diffuse albedo and diffuse albedo from no flash image, which is computed from step 1. In our ablation study, we found that bright pixels due to specular reflection is harder removed without this diffuse albedo term. Please refer to the detail of the additional constraints in the paper. We compared our method with Baron et al. Using synthetic data. For input flash-only image and depth map, since Baron et al. Estimates reflectance up to diffuse albedo, the optimized diffuse albedo contains specular reflection. while ours successfully removes specular components. We evaluated on synthetic data and compared with Zhang et al. And Bose et al. As well. Both use deep learned priors, whereas we forego this and use additional sensor depth information. Results show that ours show less error compared to GT. Note that since it's unfair to directly compare the methods that do not use depth for inference, we added random noise to the ideal synthetic depth. We also compared results of real-world objects. Considering deep learning methods use lots of priors for each parameters, results of Zhang et al. In the first row show inconsistent geometry. Results of Bose et al. In the second row show unstable SVBRDF results. Results of our method in the last row show that additional depth map helps estimate both geometry and SVBRDF more robustly. For chicken object, results of Zhang et al. Show flat normal and inconsistent depth map. For Santa object, results of Zhang et al. Again show flat normals and inconsistent depth, and Bose et al. Estimates head as gold-like material. This slide shows relighting results of Zhang et al., Bose et al., and ours. Of course, our method is not free from limitations. Since we assume the material surfaces are dielectric, specular albedo is estimated as only monochromatic and has the same color as the illumination. Second, for the saturated flash image, optimized diffuse albedo and normals show degraded performance. More discussions can be found in the paper. In conclusion, by using easily accessible devices like a smartphone, we reconstruct both geometry and SVBRDF from a single view of RGBD pair images with and without a flashlight. Thank you for listening.
Hi, Hyunjin, can you hear us?
Yes.
Okay. We're ready for any questions. I have a quick question. So since this is a flash, no flash method, does it have any requirement on the ambient light when you're doing the capture?
Yes, for the ambient light, since we assume that diffuse environment light, so the ambient light should be very small, not saturated, should not have the saturated pixels on the ambient image as well. So it's hard to adapt to the outdoor environment conditions.
Also, just another question I have is there a sort of material that you find difficult to work with this type of method?
Oh yes, since the quick tolerance we use quick tolerance model, we use the Fresnel coefficients as the constant, which means that we only consider the dielectric material. So gold-like metallic materials objects are not easy for our task.
Thank you so much. Let's give Hyunjin another round of applause. And this concludes this paper presentation session.
All right.
Thank you, Mary. So we have a coffee break now. Just a reminder that you can continue voting for the best photo of ICCP until 5 p.m. today, and then we'll be announcing the winner during the closing remarks. And for how to vote, I sent an email this morning with a Google form that where you can cast your vote, pick the best photo. All right.
hyperventilating when you're talking.
Great, thanks. Thank you everyone for sticking around to the end of the conference. So we are having our next invited speaker, Sarah Beery, giving a talk. Sarah very recently received her PhD here at Caltech, and she won the Amori Doctoral Prize that honors outstanding dissertations in computing and mathematical sciences, among many awards. She's currently a visiting researcher now at Google for the next year, that's my understanding, and will be joining MIT as an assistant professor in next fall. So I assume you're looking for students as well.
I am.
Okay, perfect. So now, while many of us like to think about, doing imaging work in the lab, Sarah likes to do a lot of work in the wild, and I mean that quite literally. So she's going to give us a talk on computational imaging challenges in ecological monitoring, trying to bridge the gap between vision, computational imaging, and ecology.
Awesome.
So thank you, Sarah.
Thank you. Yeah, awesome. So first, thank you for having me. And I think I want to preface this by saying that I don't maybe personally identify as someone who does computational imaging. I just need help with it. So, I'm going to be talking a lot about some of the different challenges we've faced when we are trying to use traditional computer vision approaches with standard sensors and realizing that probably we should actually be trying to design better sensors along with better algorithms to automate these different ways to monitor the world around us. So I guess first, why do I do what I do? I came into grad school here at Caltech with a very single-minded focus, which is that I wanted to work on bringing computer vision and ecology, sustainability, and the environment together. And that's because we're in a massive ecological crisis. Currently, biodiversity is in a more significant decline than during the last extinction of the dinosaurs. We're losing species at increasing rates, as can be seen at this plot up here in the upper left. And we've also just lost population sizes, so around 70% on average of our animal population since just 1970. And biodiversity and the environment in general is incredibly important to us as humans. So even if you guys don't love animals and plants as much as I do, you might be interested in the ways that those actually contribute to public health, to climate change, to things like food security, and ecosystem services like carbon sequestration. And I'm not the only person who wants to monitor the environment, who wants to understand how these things are changing, how climate change is affecting the world around us, and try to do our best to protect and conserve and mitigate the losses that we're seeing. Ecological data that's being collected and has been collected for hundreds of years is very diverse, but there's been a lot of modern advances in hardware that have really scaled up what people are collecting and the diversity of types of data people are collecting. So we're now using everything from satellite imagery, low-flying aircraft, this is, RGB, but also many hyperspectral bands, LiDAR, on animal sensors, so tracking individual animals and their migrations, stationary networks of sensors like cameras or bioacoustic sensors or sonar, and then we're also relying more and more on community science. Basically participatory methods that actually use passionate individuals who are not scientists to go out and collect additional ecological data using things like their cell phone. And basically, the whole classic paradigm of ecological research does not scale to this volume of data. We're collecting all of these different types of data, and they're coming in just in increasing volumes. I have a network of camera traps in Kenya, and that project alone collected 10 million images last year. And there's just absolutely no way that I, or even me and a team of undergrads, could possibly get through that data in any reasonable and sort of, in a time frame where you could actually make decisions that would help protect species if you found that something was being lost. There's over 64 million species observations coming from community scientists in iNaturalist, which is just a platform that lets people take pictures of plants and animals and upload them as occurrence records to the Global Biodiversity Information Facility. And a single aerial survey can generate something like 200 terabytes of video, and this is just a single flight, and those are doing things like trying to detect, like here, herds of wildebeest in Africa to try to understand population size. So we need computer vision and machine learning approaches to be able to combine this massive scale of data that's coming in with the ability to process it in reasonable timeframes and be able to actually act on it. And there are a few success stories. Like we have a model called the megadetector that's now being used by over 60 NGOs. We processed 100 million images last year. And all this is just a model that very reliably and generalizably is able to detect humans, animals, and vehicles in static RGB cameras. And I think this really just points to the amount of need that's out there, because, you know, one model published by a grad student really was able to like massively change the way that ecological researchers from everything from governmental organizations to research groups thinks about using camera traps and using static networks of images. But it's not always that easy. So if we look at the types of data that these sensors will bring in, the data can be very, very noisy. Very heavy occlusion. So, you know, there's elephant behind the tree. Here you can barely see a giraffe behind the tree up there. Really poor data quality, poor lighting, poor weather conditions that make it very difficult to understand what species and how many of those species you see. And then we also get vast volumes of empty data, because a lot of these sensors are using some sort of trigger, and those triggers are usually suboptimal. Biodiversity data also has a very long tail. So this means that the vast majority of the data that we have is from just a few common species. If you estimate you need around 100 images to be able to train an off-the-shelf computer vision model to recognize a species effectively, if you looked at the first 16 million species in iNaturalist, we had maybe 10,000 species that we could learn to recognize, or at least hope to learn to recognize, and another order of magnitude more that were in this very low data regime. And so this means that we have to be able to handle really few-shot learning in the computer vision sense to be able to do this well. And that's a challenge. Very insidiously, biodiversity data is just not independently and identically distributed. It just isn't, and it never will be. There is no such thing as collecting a representative training data set that is going to cover the complexity of the distribution of species on Earth. And species migrate, and those migrations are changing over time with climate change. We definitely have to be able to handle distribution shift and domain shift and generalize to things that aren't seen during training. And then not only do we have these shifts in population, we also have pretty significant bias in the data we have access to. So this is a map of global biodiversity, just alpha diversity. It's the number of unique species that exist anywhere on Earth. That's a map of the species occurrence data we have in the Global Biodiversity Information Facility. And you can see that they're almost anti-correlated. And then similarly, there just isn't a direct sensor for biodiversity. Biodiversity, I mean, people think about animals, maybe they think about plants. But, you know, this really covers everything down to plankton, you know, Lepidoptera, moths, looking, you know, in water with sonar, remote sensing data, and then all the way down to things like soil microbes. So to be able to figure out how we actually can build long-term monitoring and scalable monitoring that's going to cover the breadth of the taxonomic tree is a really interesting challenge. And then we also have heterogeneous sampling. So we do have data from all of these different data types, but they're not multimodal in the sense that you have individual samples where you have audio and images. Instead, we'll have things like daily satellite imagery, maybe every minute or so, but on an irregular motion trigger, we'll get camera trap images, and then those are sort of put into global databases, and so now you have access to those. And then humans that are taking these community science data, they're just opportunistic. So they take them whenever they feel like, and they go where people go. So you have all of these different types of data that are all complementary, but not standardized and not uniformly sampled. And then the sensors themselves, like I mentioned, are suboptimal. So this is a tweet from an ecologist who pointed out that our model helped her find the single image of an animal in 170,000 images of blowing grass that were triggered by that PIR sensor that was on the camera trap. And this is really inefficient because this means that her camera had to capture and store 170,000 images that she had no interest in. So the first kind of computational imaging question I'd like to ask you guys is, can we better capture data of interest? Can we stop capturing so much stuff that we don't need, that isn't actually very helpful, and instead do better at capturing what we actually want to capture, which might be animals in this case? So this is a camera trap. You can see some elephants there in the background, so obviously this camera trap's not helping because it's looking the wrong direction. But camera traps often use PIR sensors, and a lot of the camera traps ecologists use are off the shelf. They were originally sort of built for hunting applications, but they are cheap and reliable, and so people like to use them. But actually that PIR detectability, the motion trigger that's in these cameras, it's variable based on the size of the animal, but it's also variable based on the temperature of the skin of the animal, which means that you see much worse detection rates for reptiles, for herps. And so, one question is, can we build sensors that can capture animals across scales as opposed to needing something that's specifically looking at just temperature differentials in a really simple way? And actually, more than just trying to capture when an animal is passing by a camera, we'd also really like to try to understand what types of motion are animal motion versus background motion. So trying to build sensors that would be able to interpret styles and types of motion, understand what's background motion and foreground motion, so that we can just spend less energy and less storage capturing images we can't use. Okay, and also challenging weather conditions. So I know that there are computational imaging people who figure out how to look through fog. We have lots of images of fog, and these are, you can't see them here very well, but there's 7 endangered Grevy's zebra in this image. And so being able to get sort of the combination of sensor and algorithms so that you could figure out how to effectively categorize species even in challenging weather conditions would be awesome. And then, similarly along those veins, like, there are a lot of different ways that the environment provides challenging conditions. And so I'm going to talk a little bit about one of the projects we've been working on, which is trying to automate escapement estimation and migration for salmon in rivers, and it's looking at these static sonar cameras that are placed in rivers. These are really widely used by departments of Fish and Game and Fisheries Management. So these are all locations of these in-river sonar across just the west coast of North America. And what these are is they're multi-beam sonar. So you will have actually these, they'll put them at different distances and try to angle them just right so that they get minimal background deflectance from the bathymetry of the bottom of the river to maximize signal to noise ratio. And then they'll also choose different strata. So depending on how close to the camera you are, you'll have higher or lower resolution for a fish. And currently, there are at almost every single one of those locations I showed you, every summer, they put up a tent. They have someone sit in that tent with a clicker for upstream fish and a clicker for downstream fish. And they take 4-hour shifts, 24 hours a day. And that's how they get estimations of counts of salmon, and that's how they decide when to open and close, say, the multi-billion-dollar fishing industry in Bristol Bay. And so we want to make this process much less painful. And this is an example of what those videos look like in motion. And so we've been looking at a set of prototype locations here, all of which have some different sort of conditions, different types of, some of those different strata that we were looking at, and trying to understand whether we can automate this process. So a simple baseline we've been using, we just look at actually just frame-wise detection, a combination of a very simple optical flow included tracking, And then we use that for counts. And we use the same heuristics for counts that the ecologists use, which is basically just crossing the center line. And then we also try to measure length, because length is one of the strongest signals of speciation. And most of the time, you're actually able to determine the species of the fish that you're seeing based on their length. But there are a lot of challenges, right? You have things that are very close range and high frequency, very far range and low frequency, significant amounts of background texture, and background texture that can be moving, because it can be from sort of underwater grass. Significant shadows, and because it's sonar, if you have a shadow behind a fish, it will cause occlusion for the fish that are further away. Sediment, and that sediment changes over time based on flooding and sort of overturn and chill. And then the target density is variable based on the salmon runs. So there's a lot of diversity in what we're trying to do. And what we found is that the bottleneck for our simple method is generalizable detection. So actually, if you can get good detections of those fish in each frame, then the tracking and counting works very well. But what we find is that if we build models that work really well on a set of bathymetry reflectances, a set of different sonar bands and different scenarios, it doesn't generalize to new rivers. And so what we need is something that will hopefully be able to do this without needing to be retrained for every river that we try to bring on. Okay, so the next question I want to ask is, can we combine data from different sensors captured at different times and perspectives and actually do that effectively to get better categorization? And here we're looking at urban forest monitoring in a multi-view scenario. So this is work that we're sort of still very much in progress, but we did just publish a very large-scale data set that's explicitly trying to help us start asking some of these questions around heterogeneously sampled multi-view data for ecological monitoring. So this was a data set we published at CVPR this year. It covers 23 cities, 344 genera of trees. We have 2.6 million tree records, and then 1 million trees with associated imagery. And one of the things that's quite interesting, similar to that generalization challenge to new rivers, we see, of course, the same thing when you try to generalize to new cities. And part of that can kind of be visualized here. You can see the color is actually representing the distribution of species at a given city, and you can see how those colors are changing as you move across the US. The data is also long-tailed and fine-grained. So, I don't know how many of you are actually very good at recognizing tree species. I know that I've learned a lot about it in the last 6 months or so. And then we also have this real-world spatiotemporal and taxonomic structure. So it lets you really study, not just some sort of fixed IID curated benchmark data set, but actually study how these things change over time and understand how your methods and your models will perform in the real world. For every tree instance with imagery, we have both aerial and multi-view street level data. And what you can see here, we're showing, we've blurred out PII from that street view data to try to make sure that we're respecting human privacy. But you still have tree pixels, sky, and road. And we're interested in trying to do cross-view localization and categorization, and trying to figure out if there's ways that actually the geometric relationship between these different views can help you first better localize individual instances of trees, even though they might be taken at very different time periods. So sometimes trees are leaf on versus leaf off. Their morphology is changing as they grow. And so it's not as simple as something like NeRF, where you get many views of the same thing at the exact same time. They also blow in the wind because they just want to make things difficult. And we have found that combining information across views, even naively, is useful. And the one interesting thing we found was that the sort of value of the aerial data was dependent on species. So there are some species that are more recognizable from the air than others, which I thought was interesting. And so what we'd like to do is we'd like to be able to categorize, all of the trees in a city. And specifically, we want to build basically tree censuses, maps of trees across cities, so that we can start understanding and work with urban planners to help them make choices that mitigate things like heat islands as temperatures rise globally. I know all of us have seen pretty significant heat waves just in the last month. But one of the interesting challenges here is for our data set, we have aerial and street level views for an instance of tree. But there's a lot of trees in cities that are not visible from the street. And so one question is, can we actually detect and categorize every tree? And can we use the fact that for some of the trees, we have this higher resolution, richer data coming from the ground level to actually improve our ability to predict all the trees from just an aerial view? Second, we'd love to go beyond just species and measure health, structural integrity. So looking at actually like whether the tree is going to potentially cause property damage. And also predict growth, because predicting growth and the combination of growth and species gives you the ability to predict future carbon sequestration and future stormwater runoff, that sort of thing. And finally, we'd love to be able to use this data set to think about ways to generate realistic 3D models for every species of tree without needing to do that in a handcrafted way, requiring a lot of artist input. Yeah, so the data set has been released. And we'd be super excited if you guys are interested. Please reach out if you have any questions. And beyond that, I think there are a lot of big challenges in ecology. I talked about long-tail distributions. I talked about the fact that we're collecting sparse, biased, low-quality data. We need to be able to globally generalize. And we have these multimodal, multi-view systems. And then we also have a lot of suboptimal sensors. So if you are interested in working on some of these types of problems, I'm actively looking for collaborators, but we also have a Slack community. You can get invited by emailing AI for Conservation. It's around 1,000 researchers globally that are at the intersection of computer vision and ecology, and it's a really nice community. Cool, so thank you, and happy to take a couple questions.
Looks like we have a question coming down.
Hi, thanks for the talk. I noticed that you were looking a lot at megafauna. Have you looked at anything like insect? Because obviously insect biodiversity is a very big issue too.
Yeah, I just covered a few of the projects we're doing. But there's definitely, even here at Caltech, we have a project with a student of Michael Dickinson's, where we're looking at trying to track and look at the behavior changes of ant colonies using these static sensors. But I think the interesting thing, what I often think about is, how do we build systems that are adaptable across taxa so that they can sort of maximize impact, but also, I think the challenge is really, it's not, the computer vision is not the challenge when you're scaling to new taxa. It's the sensors, right? It's how do you sort of sustainably and effectively sense things like soil microbes or things like, rove beetle biodiversity when you cannot visually distinguish them if you're an expert by eye. The only way to tell them apart is to dissect their genitalia under a microscope.
Probably can't do that with a sensor.
Yeah, that's not my PhD.
Thanks.
Great. All right, another question? Go ahead.
Thanks very much for the talk, and it's very interesting. As you mentioned, you're monitoring every tree. You're going to create gigabytes, terabytes, a lot of data. So can you comment how do you plan to store all this data so that it can be used, for example, a couple of years later? I just have comments because I used to work for GE. In GE, there was a comment. At that time, GE owns NBC, and NBC always told us that we are losing American history because all these tapes, the data, and we are losing those data.
Yeah, no, this is a significant challenge. And we collecting this data of trees, luckily I'm doing that in collaboration with Google. And so I have access to Google scale data storage resources. But when I was looking at starting a faculty job, one of the things that I asked for was just petabytes of easy access data storage, because we work on data sets that are just massive scale. And there's a lot of really interesting open questions, I think, in sort of these areas of like even just databases and human-computer interaction, which is like you collect all this data, but it feels still to this day very inaccessible for the actual experts to be able to interact with and interpret this data, especially if they're collecting, you know, terabytes and even petabytes of video. So I feel like just as a computer science community, there's so much that we could do to try to figure out how to well, one, collect the right data in the first place, so stop collecting 170,000 empty images of waving grass. But two, how do we make like a large-scale video database something that an expert can easily query and pull out things of interest and interact with and label effectively?
So who do you think want to take the burden? Do you expect a company like a Google or the US government?
Yeah, I don't know how I feel about companies like Google being responsible for, you know, ecological data that cities need or that governments need. Governmental organizations really are stepping up here, but I think it's going slowly. So for example, the National Oceanic and Atmospheric Administration now has this large big data initiative where they're building out their own large-scale data center with a lot of GPU compute, and it's because there's so much need for these types of computer vision approaches for ecological data. So I do think that governmental agencies are starting to step up, but I think the problem is they don't have the resources of Google, and they definitely don't have the kind of ability to build out scalable infrastructure. So I think that's going to continue to be a challenge. You know, how do we take the lessons learned from Google, if they would share them, and apply them to large-scale environmental databases at NOAA or at the Smithsonian, for example?
Thank you.
Thank you. It was a very inspiring talk. The database that you mentioned, what kind of other sensors do you use? Because if you want to understand what is the situation of the trees, you need another sensors, like of air quality and pollution. And do you have these in this database, and what the size is of this database? Like what size of area?
Yeah, it depends on what you're, so I personally don't collect that type of data. There are actually a lot of sort of data products around things like air quality coming from other research groups. And so what I have done in the past is, if I'm trying to figure out how to include environmental covariates into like our studies of tree species, I pull in things like land cover, surface temperature from, you know, but the generated data products from other entities. And this is something that I've been thinking about quite a lot, which is like, is there a way? I don't know that it's that we need to have like one database to rule them all that keeps all the data for all the things, but I think what we do want is easy sort of like API to API communication to make it more efficient and more effective to be able to actually like collect, you know, given an input data point, what's the land surface temperature? Yeah, so I don't know, these are like big infrastructure problems. And yeah, I don't know, if you guys have ideas about how to solve some of these, I am all ears.
Yeah, I think we have a lot of what to talk about, yeah.
Awesome.
See you later, thank you.
Please.
Thank you.
All right, let's thank Sarah one more time. Thank you so much. Great talk.
Thanks.
That's actually also theirs. Thank you for the introduction. Yeah, of course.
Hope so.
Just press the green thing here to do full screen.
All right, so it's my great pleasure to start off the last paper session of the conference. So in this session, we have two great papers on non-line of sight imaging. The first paper is going to be titled Hidden Pose, Non-Line of Sight 3D Human Pose Estimation, and its speaker is Ping Liu.
Hi, I'm Liu Ping from Shanghai Tech University. I'm going to present our framework of long line of sight 3D human pose estimation, called Hidden Pose. Our work includes the following three main parts. In scenarios such as emergency rescue and autonomous driving, people may not be directly observed. In order to guarantee the personal safety in this situation, we need to solve the problem of long line of sight 3D human pose estimation. Nearly all existing human pose estimation techniques address the problem under the line of sight setting, which use 2D picture as input. However, in non-line of sight scene, the measurement is 3D transients, which was obtained by pulsed laser and SPAD detector. A large number of approaches have been presented to predict 3D human poses in those scenes. However, these approaches are unable to estimate human poses directly from unlost transients that differ from images and videos in those scenes. Data-driven methods in unlost have shown promising results recently. Optica convert transients into a deep feature vector at each voxel via deep reinforcement learning and estimate human poses from a sequence of action. It estimates poses from the reprojected 2D intensity feature. Embed transform the transients into 2D spatial features using a convolutional neural network and feature propagation, and then construct and classify hidden objects using a sequence of networks. It focuses on underlying objects and does not modify the network for the characteristics of the human body. We use its network architecture and estimate human pose. We present a hidden pose estimator that allows us to produce a skeletal representation of human poses in an unlost scene. All techniques leverage 3D networks with the LCT method to transform transients into 3D features and to refine the 3D features for each single shot pose estimation, without the collapse of 3D features to 2D. Pilot for unlost human pose estimation, our approach contains many deliberate designs to improve the performance. Both Baseline and Optica estimate poses from the reprojected 2D intensity feature, which loses 3D information and results in unstable results. Embed directly explores 3D features but regresses human poses in a naive way. Differently, we propose to insert a semantic light to better capture pose information, which brings a significant improvement. Data-driven methods demand large amounts of data. We use our synthesis scheme to obtain the extensive synthetic data. The scheme mainly divided into two parts. First is human pose collection. We collect human poses of real subjects using a multi-view imaging system. We gather the RGB videos and then segment the videos into frames and select images pairs under 6 views. We explore the easy mocap method to recover the 3D shape and the 3D skeleton of a human pose and feed it to the simple model.
Be a bit of a technical issue here.
Based on the
Do you have another player?
including experiment. Hi, I'm Liu Ping from Shanghai. programming rendered purpose in we can get a scatter.
Are being patient?
Pattern and match the bird.
Maybe be a little bit more patient.
We generate ground truth volumes of the human pose in binary 3D voxels using the Binh-Vox program. The second part is transient simulation. We use the rendered to get the synthetic transients based on Mitsuba 2, and for accelerate the transient render, we rewrite a CUDA programming rendered proposed in embed. Thus, we get the synthetic dataset, including transients of personalized human pose and the ground truths of corresponding volume and the joints. We also build our own confocal system for capturing real-world transients of human pose. To comply with safe use of lasers, we capture transients of 6 human poses of 2 differential mannequins as a test dataset. Our hidden pose transient dataset contains in total 47,916 human poses, including both synthetic and measured data, with 9 different motions. Motions contains not only simple motions like walking, but also complex motions like twisting poses. These poses come from 19 individual subjects. Each subject prefers 1 or more out of 9 motions. We tested our method on simulated and measured data. Firstly, we show the result of simulation data. We conduct experiment on our dataset with training, evaluation, and test. Noted that we split the dataset with different poses. Here is one relatively simple example. Compared with embed and baseline, the left foot is more accuracy. Here is another example more complicated. For the 2 poses, the 3D skeletal joints is estimated using our hidden pose estimator are in excellent agreement with the ground truths of the joints, and are markedly accurate in comprehension with the result from embed and baseline. For this pose, the 3 methods all fail because of long-regioned deformable and heavy self-occlusion. Since baseline and embed also take transients of single human poses as input and estimate skeletal joints, we directly compare with them. In contrast, Optica requires transient screens of action as input, and its human model is different from us. Therefore, we have to reorganize our dataset and realign the same human poses from 24 into 21 joints. We observed that the number of joints and positions significantly affect the pose representation. 24 joints representation is more identical to the volume. For fair evaluation, we show the results by comparing the estimated 21 joints representation of single poses selected from the screens of actions using Optica, and the 24 joints representation of the same poses estimated using our method, with the corresponding ground truths. Our estimator as well as Optica performs extremely where the geometric details in our results, such as the legs and the feet of the 2 poses, are more accurately estimated than in Optica. We test our method on real data from our hidden pose dataset. We also test our method on published real data. Further, ablation study shows semantic light has significantly improved over estimator for single-shot hidden pose estimation. In summary, we have created a hidden pose transient dataset, including simulated transients with ground truth of the volumes and the joints of hidden human poses, and the real-world transients captured from our SPAD-based unlocked image system. In addition, we have presented a tailored hidden pose estimator for 3D joints estimation of human poses in unlocked scenes. Our results demonstrate the efficiency and efficacy of our solution. We heartfully thank all the reviewers for their insightful comments and recommendations. Thank Shen Siyue, Wang Zi, Gao Tian, and Chen Wenzhen for their helpful discussions. Thank you for your attention.
If anyone has any questions, they can come up on stage to ask the authors. And I'm going to unmute myself. Just give me a second here. If no one's going to ask a question, I'll start off. Thanks, Ping, for the nice presentation. My first question has to do with extending this to video. So my understanding is that this technique for pose estimation is used on individual frames. Have you thought about the challenges to extending this to video sequences?
Hello. Thank you for your joining us. I'm sorry, we haven't got your questions because we were still watching the video. Can you repeat your question?
Yeah, I'll repeat it. So my question has to do with extending your technique to videos. Have you thought about the challenge of going from single pose, from single frame to basically an animation of someone walking around, for example?
Okay.
Yes, we are going to think about that technically in the future work. Actually, we have thought about it a little bit, but haven't got to very the results yet, and we are going to work on that. Thank you very much.
Okay. And another question actually as well. So my question has to do with different body shapes and sizes. So have you thought about what are the challenges, or have you tested this technique on a variety of people of different heights, different ages, for example? Does the technique work for both kids and adults, for example?
All data was from maybe different shapes of people, and we have different ages. But we do not have kids on our data set.
Okay. And I'll ask one final question. So in your technique, although everything's hidden around a corner, you have full view of the person's body. A lot of the time, perhaps there might be some self-occlusions, or someone might be walking behind a desk, or maybe turning around in such a way where you don't see maybe an arm. What happens in your case when that happens?
Our data was collection was around the center of our detector, and we do not perform position the detector in our technique.
Okay. Great. Thank you for the answers, and thank you for your talk.
Thank you for your questions.
All right. So our final paper is going to be another virtual presentation. And in this case, we're going to have a talk again on non-line sight imaging. It's called Physics to the Rescue, Deep Non-Line Sight Reconstruction for High-Speed Imaging. And this talk is going to be given by Fangzhu Mu and company.
we present a learning-based method with strong physics priors to address the challenges in high-speed non-line of sight imaging. Non-line of sight imaging aims to uncover the shape and appearance of objects beyond the direct line of sight by analyzing the propagation of light through the hidden scene. The most successful approach to non-line of sight imaging is based on the time-of-flight principle. An imaging system raster scans a Rayleigh surface with pulsed laser and captures multiply bounced indirect light reflected off the Rayleigh surface using time-resolved sensors such as single-photon avalanche diode, or SPAD. The picosecond resolution time dimension of SPAD histograms encodes rich information about the geometry and appearance of the hidden scene. Consequently, the central question in non-line of sight imaging is how to invert such measurement to reconstruct an image of the hidden scene as if being captured by a line of sight camera from behind the Rayleigh surface. The standard image formation model for non-line of sight imaging introduces several approximations for the ease of analysis. For example, it only models 3-bounce light without accounting for higher order scatterings. This simplified model forms the basis of physics-based reconstruction algorithms and, importantly, is adopted for the rendering of synthetic datasets for training deep neural networks. But to what extent does this model capture the nuances in data collected by real imaging systems, especially those optimized for acquisition speed? To answer this question, let us do a quick reality check. On the left is a measurement of digit 2 rendered by a transient rasterizer, which runs at interactive rate and thus enables large-scale data simulation. On the right is a measurement of a similar scene captured by real hardware. Note the striking difference between the two datasets. The real sensor response is bumpy, noisy, and most notably exhibits distinctive vertical stripe pattern. So where does this pattern come from? It turns out that the stripes are the byproduct of a hardware trick known as pixel remapping, which is key to rapid data acquisition. The idea behind pixel remapping, as we illustrate on the left, is to scan a Rayleigh surface with a sparse pattern and record data using a pixel array, and later map the pixels to skipped positions between the scan lines to fill the gap. Pixel remapping reduces laser scanning time by an order of magnitude, resulting in an unprecedented imaging speed of 5 Hz at the expense of varying degrees of geometric error shown on the right. How do existing reconstruction methods behave in the presence of such error? We focus on methods for non-confocal reconstruction, as pixel remapping is only implemented with non-confocal imaging hardware. Please refer to our paper for a comparison between confocal and non-confocal setups. Phasor field RSD is a physics-based method based on diffractive wave propagation. While it is fast and robust to the approximations, it is limited by sampling rate and hence yields blurry reconstruction. On the other hand of the spectrum are learning-based methods including LFE and neural transient fields. They are exclusively trained on synthetic data as it remains infeasible to collect real data at scale. While these methods behave strongly on synthetic test data, they cannot account for the large domain gap and thus fail to generalize on real captures as we demonstrate later. Further, neural transient fields require lengthy per scene optimization and cannot learn statistical priors as in feed-forward methods. LFE, on the other hand, supports feed-forward inference yet lacks a physically interpretable scene representation and cannot learn from transient measurements as neural transient fields do. In this work, we attempt to address two key challenges for learning-based non-line of sight reconstruction. With only synthetic data available for training, we seek a carefully designed model that is robust to the approximations in light transport and hence can generalize well on real captures. Meanwhile, we hypothesize that a diverse set of supervision signals encourage the learning of holistic scene representations for better reconstruction. To this end, we seek a unified learning framework that supports diverse training objectives. The two challenges end up with the same solution, which is to combine physics priors with the power of deep learning. We now present our method. Our model embeds physics priors into a deep model to regularize its solution space. It includes three main components: namely an encoder that maps a transient measurement ht to a feature volume cs, a conditional radiance field that predicts the density and color at every 3D point given its feature vector, and a volume renderer that converts the radiance field into intensity images, depth maps, or transient histograms for training and inference given their respective forward rendering models. We now dive into each of the three components and highlight the key modeling decisions. Our encoder design is inspired by RSD, which transforms an impulse response of the scene into an intensity volume using diffractive wave propagation. Unlike RSD that operates on raw measurements, our encoder first learns to extract an XYT feature volume from the measurement and interprets it as featurized impulse response, which is subsequently transformed by RSD into an XYZ feature volume. Our encoder inherits the robustness of RSD and regularizes the learning of subsequent model components. Finally, our volume renderer queries the radiance field and synthesizes the desired target. One key strength of the physics-based volume rendering framework is its flexibility with respect to the forward rendering model. This allows our model to explore diverse training signals, including intensity images for supervised learning and transient histograms for unsupervised learning. For supervised learning and model inference, we adopt the same rendering integrals as NeRF for the synthesis of intensity and depth images. For unsupervised learning, we introduce a novel transient rendering formulation for the synthesis of transient histograms. The mathematical details are beyond the scope of this presentation. Please see our paper for more details. We now turn to the training of our method. Our learning objectives are a combination of reconstruction and regularization terms. Thanks to our flexible volume renderer, our model can learn to reconstruct intensity images using MSE loss or reconstruct transient histograms by maximizing the Poisson log likelihood. Additionally, we apply a beta prior on the cumulative transmittance to bias array towards either hitting or missing the object, and a total variation prior to eliminate spurious density of floaters in the reconstruction. At inference time, our model renders intensity and depth images of a scene in a single forward pass. The runtime of our method far exceeds the data acquisition rate of the hardware. The main bottleneck of our method lies in the volume renderer, which accounts for 80% of the runtime. We anticipate that our method will benefit from efficient rendering techniques in the NeRF literature. We now present our experiments. We first qualitatively compare our method with prior arts on synthetic data. All learning-based models are trained on a synthetic dataset of alphabets and digits and are evaluated on unseen objects from the same dataset or training objects with unseen poses. Our models produce sharper reconstructions and can sometimes recover invisible scene geometry indicated by the arrows thanks to the learned scene priors. Additionally, our method, despite not being trained on ground truth depth, can render plausible depth maps with the versatile volume renderer. Next, we report quantitative results using widely used metrics. On the alphabet dataset, our model trained with the two reconstruction terms combined consistently outperforms the baselines and other variants trained with a single reconstruction term. This highlights the strength of physics priors for learning-based reconstruction and validates our hypothesis that diverse training signals promote better reconstruction. To assess how the models generalize on out-of-distribution data, we challenge them on scenes with more complex geometry. As shown on the bottom, our models are worse than NETF++, a variant of NETF using our proposed transient rendering recipe. This is completely expected, as the learned scene priors fall short in the presence of a domain shift and start hurting the performance. Nevertheless, the result shows the superiority of our transient rendering recipe, as NETF++ performs much better than NETF on complex objects. Most importantly, we compare our method with the baselines on real captures. As a reminder, real data look very different from synthetic renderings, and present significant challenges to learning-based methods that are typically sensitive to domain gaps if no special care is taken. As expected, LFE, NETF, and NETF++ all exhibit noticeable artifacts as they are not designed to guard against approximations in light transport. While RSD, despite being more robust, produces blurry images. In contrast, our models render crispy, artifact-free intensity images and recover plausible depth. This highlights the importance of the physics priors that prevent our method from overfitting the synthetic data. In summary, we present a deep model with strong physics priors for high-speed non-line-of-sight imaging. Our model consists of an encoder that embeds RSD for feature transformation, a conditional radiance field that learns scene priors from data, and a volume renderer that can flexibly render different targets for training and inference given appropriate forward rendering models. Our unified modeling framework enables learning from diverse supervision signals, supports fast feed-forward inference, and most importantly, generalizes well on real captures that approximate light transport in various ways. Thank you for listening.
Once again, if anyone has any questions, they can feel free to come up on the stage so that the authors can hear them. Please come to the stage to ask your question. All right, how do I unmute my audio? Go ahead.
Okay, my question is, well, thanks for the talk first. My question was about the first stage, when you perform a 3D convolution over the input data, which is the impulse function. Are you performing any filtering over that function before that, or is it directly, I mean, the filtering is implicit on the 3D convolutions?
My question, well, thanks for the talk first. My question was about the first stage.
My understanding is that you're asking about how, in the first stage, the filtering or the filters are learned, right?
Yeah. You perform a 3D convolution after, over a set of feature extraction over the impulse function at the beginning. Do you filter the impulse function before that 3D convolution, or the filtering is implicit over all those 3D convolutions there?
Oh, yeah. So I don't think I have any filtering before RSD. So basically, we run two 3D convolutions, both learned on the raw transient measurements, and then do this wave propagation directly on the learned features. So there's no additional filtering step.
Okay, and another, this is out of just curiosity, how do you preserve, because you perform a RSD propagation over those extracted features, how do you preserve dimensional information? Because you need to interpret what those features mean for an RSD, right? The RSD has to deal with dimensions.
Yeah. So for RSD, essentially we propagate each feature channel independently. So just treat every feature channel as some sort of measurement and use RSD to propagate it into the spatial domain. Yeah.
Okay, but those features have some sort of dimensional information. They are not just high dimensional or high level features of the, right? I don't know if my question, I will maybe rephrase it. So if you perform a lot of convolutions, then the meaning of the features may not preserve the raw dimensional information that the original impulse function has. That's just my question. So how do you preserve that information there?
Yeah, I guess this part, I wasn't totally sure. I guess essentially the network learns to extract features, and RSD kernel itself is fixed. So I assume that the network will learn to extract features that RSD can propagate, and after propagation, the features will carry some meaning for subsequent reconstruction. But I think the same idea was also kind of popular in standard steady-state rendering, like in NeRF type method. So it's not like
Okay, thank you.
Great, thank you once again. And let's give a round of applause for the papers of this session.
Thank you.
Oh, it should.
Right, hello everyone. My name is Emma Alexander, and I'm so excited to introduce our final speaker, final invited speaker of this amazing conference, Professor David Van Valen. David received his bachelor's in both math and physics from MIT, his PhD in applied physics here at Caltech, and then also an MD at UCLA. So he applies this incredible depth and breadth of knowledge here as a professor of biology and bioengineering, where his group combines imaging, genomics, and machine learning to better understand biological systems in a perspective that I think is really exciting for our community. He considers living things in terms of how they process, store, and transfer information. So today he's going to be telling us about the real challenges and potential of microscopy in this modern view of biology, and share some advances that his group has made on this. So please join me in welcoming David Van Valen.
Can folks hear me? Yeah? Thanks for the very kind introduction. It sounds great on paper, but I assure you I spend most of my time responding to emails and putting out fires. So today I'm going to talk a little bit about my lab's work at this intersection between biological imaging, deep learning, artificial intelligence, and we're very excited about what we've been up to for the past few years. And so with that, I'll get started. So I'd like to actually start with a 30,000-foot view of the intersection between machine learning and biology in general. And so the way I like to think about this intersection is in forms of types of data that are generated about biological systems. And so roughly speaking, there are three kinds of data that are out there in the community. There's imaging data. My personal favorite gives you information about the spatial and temporal variation of living matter. There's sequence data, and so this data really gives you information about the parts list variation of living matter, which genes are present, which genes are turned on, which genes are turned off, and whatnot. And then there's structural data, and the structural data, really tells you how biological molecules interact with the physical world to give rise to biological form and function. And so what's happened over the past few years is that for each one of these different data modalities, there's arisen a collection of deep learning, AI, whatever you want to call it, methods that can do really remarkable things with these sorts of data. So for imaging data, there are convolutional neural networks, which is mostly what this talk is going to focus on. Although, yes, there are vision transformers that can do equally amazing things. But for these other data modalities, there are other algorithms, other architectures that have been equally transformative. For sequence data, there are large language models. So this figure is taken from one of my favorite papers of the last couple of years by Brian Bryson's lab at MIT. And what they showed in this paper is that by taking large data sets of viral sequences and using large language models trained in a self-supervised fashion, they could actually get these models to understand which sequences can evade detection by the immune system, which ones are likely to be less pathogenic, which ones are likely to be more pathogenic. And then for the structural data, they're equivariant graph neural networks. Unless you've sort of been living under a bridge, you're sort of aware of the advances that have been made in this space that have really unlocked some very nice advances on the protein folding problem. So most of this talk is going to focus on imaging, but I just like to highlight this because this is the context within which the work that I'm describing is taking place. Okay, so for imaging in particular, I think the reality is that deep learning is just really changing the relationship between biologists and imaging data by making it easier to access quantitative information that's present in images. And so a variety of tasks, quantitative tasks that were very hard, have been rendered, I don't want to say like they're easy, but they're manageable now, and a collection of them are shown here on the slide. And so we have a task of segmentation. And so in this case, identifying individual cells and images. There's a task of object tracking, so tracking cells across different frames if you're collecting live cell imaging data. There are tasks like spot detection. So if you're doing single molecule imaging, you'll have these images of fields of views of different spots, and the analyses that you want to do invariably require identifying spots in these images. And then there are also some more imaginative applications, restoring noisy images, interpreting label-free images, and whatnot. And so what's really exciting about this intersection is that, when you take what can be done now with the algorithms, which can be viewed as taking information out of images, and then you compare that with the advances that have been made in measurement technologies, imaging technologies, which lets you encode more information into images, then, there's the possibility of just being in this world where the microscope is the biologist's tool of choice, because quite literally anything that you'd want to be able to measure, you can measure with a microscope. You have access to the spatial variation, the time variation. There are methods now that give you access to the parseless variation. And if you're doing everything on the same sample on the same microscope, then you sort of have this opportunity to integrate information across these different measurement modalities. So if you're, for example, if you're interested in gene expression or where different proteins localize, or how the dynamics of signaling pathways change over time, you could conceivably do all these experiments on the same sample with a single microscope. So this is sort of the big picture vision that's been driving my lab for the past few years, and well, okay, it's going to be more than the past few years. Let's just say it's probably going to drive the next 2 decades of my life. To really make this happen, what you need are computational primitives. And so by computational primitive, I mean it's an algorithmic black box that can just do something and do it well, robustly, and generally, so that you don't really have to worry about where your imaging data is coming from, right? So whether you're looking at it for, let's say, a given task like identifying cells, having a computational primitive that just doesn't care, okay, am I looking at tissues, or am I looking at cells in cell culture? Am I looking at mammalian cells, or am I looking at bacterial cells? My data came from a Leica microscope, or came from an Olympus microscope, or a Nikon microscope. Having these units that can just do things and not really care so much about those details, that's really what this biological imaging field needs. And then also I'd add, if said primitives exist, one might want to rethink about how you're doing your experiments to take advantage of this new functionality to design better, more scalable experiments. Okay, to hone in on this idea a little bit more, to be concrete, I have this toy example of what we'd like to be able to do. So here we have a textbook, a classic movie from a cell biology experiment, where you've got a blood smear. You can see an immune cell called a neutrophil in the middle, and what this neutrophil is doing is it's executing a search for a bacterial cell, right? And so you can see these wiggling black dots in the background. Those are bacterial cells, and then eventually the immune cell finds it, engulfs it, and then eats it. What we would like to have are deep learning systems that can take in this raw data and produce a narrative very much like what I just described about what's happening in these data. And so you can go through a thought exercise of how to do this. The very first notion you might want this deep learning system to understand is the notion of like what's a cell, right? And so it should be able to understand that this is a cell, that's a cell, these wiggling black dots are cells. It should understand conservation of identity over time, right? This is a movie stack, and so it should know that, okay, if I see the cell in frames 1, 2, 3, 4, and 5, those refer to the same object. And you should be able to extract information about what they look like, where they are, et cetera, et cetera. But that's not all you'd want it to know, right? And so there's this layer of semantic information, prior biological knowledge that's also present here, right? And so this includes notions like the different cell types, right? So it should know that these are red blood cells. It should know that this is an immune cell. It should know that these wiggling black dots are bacterial cells, and then it should also be aware of interactions that are happening in this movie as well, right? So it should know that there's really no meaningful interaction between the red blood cells and everything else, and it should know that between this particular immune cell and this particular bacterial cell, beginning of the movie, there's this interaction which represents a search called chemotaxis, and at the end of the movie, there's this interaction, the eating called phagocytosis. And so, concretely, what these computational primitives are meant to do is convert these raw imaging data into a format that you can actually, search and understand using computation, like the spatial temporal graph that I just described. Where every relevant entity is a node in this graph, and then you can have node-level features like cell type, location, appearance, and then edge-level features which denote the relevant interactions. Okay, and so this gets into this is what we want. The question is, how do we build it? And so this gets into the title of this talk, which is that everything is code. And this is just a snarky way of saying, which everybody knows, that if you want to be able to build these things in practice, you actually need much more than just the deep learning, right? You need the data and the labels to power the models. Obviously, you need the models, but then you also need the computational infrastructure for training and inference at scale. And so, in sort of our view, which is not really that heretical anymore, you shouldn't really be working on one of these problems in isolation, but rather you should be working on all of them at the same time. And so instead of thinking about, hey, I want a model to be able to do something, so let me just build a data set, or working on model architectures, or working on software to make things accessible, really you need to be co-developing data sets, co-developing models, and co-developing computational computational systems for making these accessible. And the challenges in each of these different spaces, can really just be thought of as software engineering problems. Okay, so with that introduction said, I just share a few vignettes that are coming out of our lab. The first two focus on identifying cells and images, which is a common challenge for our imaging experiments. So in our lab, we like to collect live cell images. We like to collect movies of living cells, so we can get a sense of what they're thinking. So we have these cells. We'll throw in some biosensors in there that will change either the amount or the location of the brightness in response to what the cell is thinking about their environment. And so you'll get these really nice movies, and so what I hope you can appreciate is that you'll have a change in the location of brightness from being in the cell nucleus to being on the cell cytoplasm. And to quantify these sort of data, what you need to do is identify cells in every frame, link these detections together over time, and then ask, okay, how bright is each compartment? And if you can do that, then you can convert these movies into quantitative data like this. You need to be able to identify cells to be able to make this interpretable. Similar challenge occurs for folks who look at images of human tissues, which is relevant if you're trying to understand the pathogenesis of disease. And so there's really nice imaging platforms now where you can quite literally collect a 40-color image of a human tissue, where each color corresponds to some biologically meaningful variable. To analyze these data, right, and so here you can see a sort of example data set taken from a paper published in Cell by colleagues a couple years ago. And so you see here is 4 different patients and about 7 different markers, or quote-unquote colors, and each color corresponds to some biologically meaningful thing. So for example, CD45 highlights where all the immune cells are, EGFR and P53 reports on the state of different cancer cells that are present, and whatnot. So to be able to render this data interpretable, again, what you have to be able to do is to go into images like this, identify where the cells are, and then if you identify where the cells are, you can ask, like, okay, well, how bright is it in each color, do some clustering, identify cell types, identify spatial patterns. If you have outcomes information, you can link those patterns to patient outcomes and whatnot. And so across these different flavors of experiments, identifying cells is just a common challenge. And really what's needed in these two spaces are computational primitives that can do this task for us. For the tissue images, what's needed are algorithms that can just look at them and say, okay, here's where all the cell nuclei are, then also here's a guess at the contours of the entire cell. And then for the live cell imaging movies, what you need are algorithms that can not only detect things in each individual frame, but link those detections together over time. And so that's what's needed. Question is, how do we get there? And so when we started, this space was actually fairly immature. And what we realized is that the need for data sets actually far outstrips the needs for algorithmic improvements. And so this just was where the field was when we started. And then also, I'd say this stemmed from an observation that we'd made over the past over the years when we've been doing model R&D, which is that oftentimes the reasons why models don't perform is because the either the underlying data itself or the associated labels lack the information necessary for the model to learn how to perform the requisite task. For imaging of tissues, this issue arises a lack of contrast between neighboring cells and tissues. For the live cell imaging data, this arises a lack of temporal information in existing training data sets. Just so happens that most of the existing data, if there's a variety, that's been labeled, have been of static snapshots. Very few data sets exist where people have actually gone through and tried to label entire movies. And so example of what I'm talking about of improving model performance by improving the information content of data is shown here. And so, here we have an image of cell nuclei, and what you can do is, have some graduate students go through, label what they think are the cell boundaries, train a model, and then run said model over this image. And what you get are images that sort of look like this. And what I hope you can appreciate is that there are all these gray regions that you can see. So for example here, and these gray regions sort of represent areas of uncertainty where the model just doesn't have the context clues that it needs to understand, like, where's the boundary between two neighboring cells. If you're doing this multiplex tissue imaging, you can actually add this information back in the form of additional stain, right? So you can stain for the nuclear envelope, add in that contrast, do the same thing where quite literally everything is the same, except now the model has access to both the nuclear stain and then the nuclear envelope. And so when you do that, what I hope you can appreciate is that many of these gray regions, they magically disappear. Okay. And so what we've done is we've just gone through for each of these domains, compiled large amounts of representative data for the tissue images. These are representative data of both cell nuclei and then also cytoplasmic or membrane stains. For the live cell imaging movie, these are movies of cells that people commonly image. And with these large collections, the major task is annotation. Just like to show a montage of what some of this looks like, so you can get a sense of how challenging this is. For the tissue images, the big challenge is cell morphology, which varies quite drastically across different tissues and even within the same tissue. On top of that, you have signal to noise and autofluorescence characteristics across different imaging platforms, and then you also have some other artifacts as well. For the live cell imaging movies, the major challenge here is time. Producing segmentations or labels that are temporally consistent, and then also having a labeling framework so that events that happen, like cells dividing, cells dying, you can capture those in that labeling framework as well. So here we see an example of when cell division goes wrong, sort of the textbook story that you might read in a cell biology book about one cell turning into two. When you're imaging immortalized cell lines, this is not, that might be the majority, but there's a large number of these sort of edge cases that happen, and they're interesting enough where you want to be able to catalog them as well. So that's the challenge, of difficulty, but then there's also this issue of scale. There's just too much data for humans to ever be able to annotate, and so what we've turned to is image labeling through human AI collaborations. And so we just realized that it's too hard for the humans to do on their own. It's too hard for the AIs to do on their own. We need them to work together, and so that means that the challenge then is building software systems to enable this human AI collaboration. And so we've had a super talented software engineer in our lab, Tom Doherty, who sort of set out to build exactly such a software system. And so the result is a software tool called Deep Cell Label, which is browser native software for distributed labeling of large biological image collections. I'd say sort of inspired by a lot of the stuff that's happened in the self-driving car space, but with an eye towards the unique phenomenology that you see in biology, right? It's very, well, I don't want to say like it never happens, but in these self-driving car data sets, you're not going to see car A eat car B, but you'll see that when you're looking at cells on a microscope. And so with the software, we're able to get large data sets labeled either through experts who exist in our lab or through crowdsourcing vendors. Because it's browser native, we're able to access crowdsourcing, and so we we've thought a fair bit about how to do this. And the solution we sort of arrived at is sort of human-in-the-loop labeling, that occurs in three phases. First phase, experts sit down, craft a preliminary data set preliminary model. This model then gets passed off to the second phase where where crowdsourced workers create new labels by fixing model errors rather than creating labels from scratch. And by having them work in this way, you're able to reduce the marginal cost of annotation, because as the cycle runs, eventually you retrain the model gets more accurate because it's just seen more data, and because the model's more accurate, you end up having to pay less for the next additional annotation, simply because there are fewer errors that need correcting. And then the third phase, you run this long enough where you have enough data where you can train a model on the full data set and release it to the community. And so this work was published in Nature Biotechnology earlier this year. We ran this method on our tissue imaging data that we had compiled to create a data set called TissueNet. Contains approximately 1.2 million paired nuclear and whole cell labels across a wide variety of different imaging platforms and tissues. It took about 2 person-years to generate, because we did it in this crowdsourced way. It actually, the real amount of time was substantially less, and the amount of that 2 years that was borne by experts was a small fraction. And so the really nice thing about training models on such a large data set is that they generalize. And so here we see a collection of 12 different images taken from a held out part of TissueNet. And so here we see the results on cell segmentation produced by a model that was trained on this diverse data set. And so there's a visualization where it sort of colors each cell by the relative error in size, and then also there's an associated F1 score. And so this was quite impressive when we first saw the results. So much so that we actually did the effort to make the comparison to humans, and the analyses that are detailed in this paper led us to conclude that this algorithm trained on the full data set, which we're calling MESMER, is able to identify cells with effectively human level accuracy, which is the first time an algorithm has been reported to do that on this task. So right now we've been busy sort of setting this infrastructure loose on our live cell imaging data set. And here again, like the challenge is the time dimension, is getting both cell detections and then also cell detections to be temporally consistent, but then also to be able to track things over time. And this work is still ongoing, but our early results are quite good. And so we've developed a couple new approaches for doing segmentation and also cell tracking, and you can see the results of them here. And so here we have 4 different cell lines. I believe top left, raw 264.7 cells, HAC293 cells. I believe those are NIH3T3 cells, and then those are HeLa S3 cells, which you're seeing are a fluorescent marker of the cell nucleus. And you can see the algorithms that can do the segmentation and also the tracking. And so these work particularly well at identifying division events and helping you construct cell lineages. Other computational primitives we've been working on are spot detection. This is a very important problem for spatial transcriptomics experiments where you're trying to measure gene expression in a way that preserves spatial information. And so the way some of these measurements are done, you'll basically perform a series of single molecule imaging experiments. And so what you have to do at the end of the day is in each round of imaging, identify the spots, and then you have to link these spots together over time, so over your imaging rounds, and then determine, okay, which detection events correspond to which genes. And so the spot detection is currently I don't want to say it's an unsolved problem, but the way in which it's done now requires an inordinate amount of manual fine-tuning for each data set. And this is really like a data problem because these data sets contain quite literally millions to billions of spots, far too many for humans to ever curate. And so what we've turned to solve this problem is weakly supervised learning, where we sort of take all of the classical algorithms that are commonly used and a representative data set, fine-tune these classical algorithms on these data sets to produce a series of predictions, and then we perform generative modeling to create a consensus prediction, and then once we have this consensus prediction, we can then train deep learning models to do spot detection. And what we found is that this approach works substantially better than anything else we've tried, including other deep learning approaches where you train on either simulated data or data generated by just one of the algorithms. And because this algorithm generalizes, we can combine it with some of our other algorithms for cell segmentation to create these universal pipelines for analyzing both singleplex and multiplex fish experiments. And so this is the results of some of those methods. We've also worked on scalable cloud-native software for deploying these models at scale. This was published in Nature Methods. I won't belabor this point too much. Just to say that this software sort of works like how Netflix works. People come home at 5 p.m., demand goes up, and so what Netflix does is they just spin up more servers to serve their movies. This software works in very much the same way. As more people start pinging the server, it's aware of that, and so it scales up the computational resources. Okay, and so that's almost it. I just want to give a little couple slides about where we're headed, and that's towards universal models for cellular imaging. And so you sort of saw some models for tissue images, some models for cell culture images. We're not the only folks active in this space. There are people who develop models for bacteria, archaea, yeast, et cetera, et cetera. And so what has ended up happening is that for each one of these different domains, people generate like their own data sets and their own methods, and it's non-trivial to get a single model that could actually work on the diverse array of images that are out there. And it turns out that the biggest limitation isn't so much in the deep learning methodology, but it's how the very notion of what's a cell is being represented to these models. And so these three these three different wave representations, be it edge interior background, sort of deep watershed representations, mass Gaussian and whatnot. These of all the cell segmentation methods that are commonly that are in production now, they're one of these methods, and they're just limitations. So one, what people do is they sort of pick a representation that is fine-tuned to the data set they're looking at. But two, there's also just an underlying limitation to this approach. And for the two-dimensional cellular images, a big limitation is overlapping objects. So when you're looking at movies of cells, or if you're looking at cells and tissues, it's very common to have cell A crawling on top of cell B in both cases. And as you can imagine, none of these approaches are going to be able to do it. But this is such a fundamental problem that even the format within which people label these images doesn't account for this phenomenon as well. And so this is to properly address this. This is really a full stack machine learning problem where you need to address the labeling software, the labeling formats, the way you're framing your instance segmentation problem, and then the flavor of model that you're using. And so because we sort of built this infrastructure, we have control over everything. We can do that. And so here's a prototype that Tom put together where we can label images using a format that allows for overlapping objects. And one of our postdocs, Uriah Israel, in working with a graduate student with Pietro Perona, have been busy exploring porting over the new transformer segmentation methods that have come online in the past 6 months or so. And the real nice thing about these methods is they do not have this limitation about the representation. And so here you can see objects that are sort of like round and globular, or things that are long and filamentous. The same model is able to learn like what they are. And so there's a fair bit of work that has to get done to make these sort of usable for biological imaging data. But we're pretty excited about where this is heading. And so with that, I will stop talking. And so a huge thanks to my lab, who they're entirely responsible for all of this stuff that I presented today. And so you saw contributions from quite literally everybody who's currently in my lab, as well as some alumni. Big thanks to collaborators, Michelangelo, Liat Karen, Long Kai, Yisong Yu, and then also Eric Osterman on a Cloud Posse. And then lastly, I have to give a big thanks to our funders for supporting this work.
Wow. Thanks, David, for sharing that amazing talk. Folks can come up, and I think we have time for a few questions.
Hey, thank you for the talk. It was really nice. So all of this was cell size level, right? Of the order of, say, a few microns.
Yes.
What are the challenges that you would need to face if you were to go to the size of virus, for instance? That would be like 3 orders of magnitude smaller than this. Essentially, my question is how long till someone takes a picture of my throat and I get a COVID test?
How long till someone takes a picture of what?
Of my throat and I get a COVID test.
Oh, I don't think you'd want to do that with imaging, though, right? Like, I'd say like there's sort of this problem where, you know, if you have like a fancy hammer, like everything starts looking like a nail. And I'd say like diagnostics, while there is certainly a space for that for cellular level imaging, for diagnostic testing of like a virus, like I'm not sure that's like the best thing to do. So depending on the assay, you know, the short answer, there's like a, well, the short answer and long answer. Short answer, you know, you could put together an assay, imaging based, that could do it probably on the order of like a couple of months. Likely be like some like fluorescent in situ hybridization method, where you're targeting different viruses with RNA probes. But there, it's like, what's the advantage of the spatial information? I don't think the spatial information really would give you that much. Really, just want to know is like, is the virus there? Is it or not? And is it replicating? Right, and you can get that with non-imaging assays.
Yeah, thank you.
Yeah, thank you for the great talk. I was wondering that you were talking about doing all these software primitives that obviously you've done a super great job on working on. Do you foresee this kind of becoming one kind of software package in the future, or will it kind of continue to be individual things that people use?
That's a good question. You know, like we sort of have this DeepCell brand, which unfortunately a startup company named DeepCell that also uses like AI to do cellular imaging popped up after you know, a couple years after we started working on it. And by the time I realized it, you know, it was sort of too late to do anything about it. But loosely, the way I like to think about it is that these are a collection of software tools for doing full stack development of machine learning methods. And so if you're operating in a space where, you know, the training data either like doesn't exist or is sparse, having like models that are sort of out of the box or capable of doing certain things, and the sort of hyperparameters that you might need to tune are transparent and, you know, quote unquote accessible. And then, you know, let's say like you have something that works well enough where you feel like, hey, you know, I need more than just a Jupyter notebook, you know, let me put a pipeline together in the cloud, and do so in a way where, you know, the pre-processing steps, the model and the post-processing steps are, you know, fairly transparent, where if you need to, you know, scale things out to images of different sizes, there's a path to being able to do that. And, you know, the scalability is just like intrinsic to the software system. That's kind of how we see it. You know, it's, you know, doing this, I'd say like industrial scale machine learning on an academic budget is not easy. Unclear like how long this will continue. At very least, like, you know, the next few years, at least until we can demonstrate that these harder labeling things and these harder machine learning, or getting machine learning models to sort of recognize phenomena in this interpretable way. You know, we've sort of done that, but, you know, in like 5 or 10 years, like, you know, like every academic software package, like who knows, right?
Thank you so much.
Hi, thanks for the talk. As a non-biologist, I was just sort of curious, like, let's say tomorrow you've completely solved this problem of like having these machine learning primitives for like, for example, cell segmentation or maybe identification, and it just works perfectly. What are some like exciting problems that you would be able to tackle now with these like new tools?
That is a good, that's a good question. So the short, yeah, so the answer to that question like bifurcates, and the bifurcation is this going to be an industrial application being funded by a variety of different VCs, or is this going to be an academic application that's being funded by academic-sized budgets? And that really, I'd say, just determines the nature or the scale of the experiments that you can do. So on the academic side, you know, what we're trying to do is we're trying to sort of combine this image-based phenotyping, where you have these easy deep learning-based primitives that can read things out, and combine that with perturbations. And so one of the things that we're working on in our lab is a easy way of imaging populations of cells where each cell has received like a different genetic perturbation. That's not an easy problem because without rendering it visible in the microscope, there's no way of knowing a priori, okay, which cell received which perturbation. So we've been working on a wet lab technology that should hopefully make that step easier and more scalable, or let's say like accessible than it currently is. And so if you can do that, right, so then it's okay. We can perturb everything at genomic scale, and then for phenotyping, we can phenotype with single cell resolution. We have all these different imaging assays that you can add on top. Looking at gene expression, cell morphology, protein localization. And if we're able to do the live cell imaging analyses properly, then we'll also have access to dynamic phenotyping as well. And so there, I think there's just like a wide range of different biological phenomena that you just couldn't explore the genetic basis of because of these myriad of technical reasons. For the industrial applications, it's not very imaginative. Either you're trying to generate new drugs against existing targets, or you're trying to find new targets that people don't know about. Either one of those two things.
Thank you.
Yeah.
Hi, thanks for the talk. So we've seen in other domains human labeling has gone a long way, and then in recent times, and I think in a growing way, we're seeing a lot of synthetic data coming in for modeling more complicated aspects of the underlying things that you want to model or data you want to extract. Do you think that's going to come in this biological context in a similar way?
I'm not sure. So I would say the experiences we've had using synthetic data have primarily been in the spot detection space. And I would have imagined there that, by either approximating the point spread function or programming in the point spread function for our microscopes and using that as a generator for spots, we would have performed comparably or better than than the approaches, the data-driven approaches that we've been developing. Turns out that's not the case. And that models trained on real data where you sort of did this weekly supervised learning to get some notion of what's a spot perform better than the models that are trained purely on simulated data when benchmarked on simulated data, right? Because if you don't have human curated labels, right, you have to come up with clever ways of benchmarking performance. And so I'm not sure. There's just a lot of artifacts that exist in biological imaging data. It's not nearly as clean as people like to imagine. I'm a big proponent of keeping having your data sets reflect what you actually want to process, what you actually want your models to perform on, and that's different than data sets that are collected for XYZ machine learning competition, because usually you take those artifacts and you screen them out. So that said, it's definitely possible, but intellectually speaking, I don't think it's likely that I'm the person to do it. We're probably just going to nail out a few more computational primitives and then do a mic drop and move on to other things.
Well, thank you so much, David. Unfortunately, I think we're going to have to save the rest of our questions, many fascinating discussions to come, to offline. But let's all please thank David Van Valen again.
So we've reached the end of our 3 days here at ICCP. It's been a lot of fun. It's so great to be back with you all in person, get to see old friends, get to meet new people. And so thank you all for coming all this way. Before we end, well, we have a few announcements. We have some awards to give out, which we're excited to do. But before that, we just wanted to go through, again, some acknowledgments, because without all these people that you see here, this conference wouldn't have come together. everyone here, was essential, but I do want to also call out a couple people that really, especially in the last weeks leading up and in the final and in the days here, have been so helpful. So Seren, behind the scenes, has been absolutely amazing, keeping us on track, trying to figure out the finances and everything, and he really was fantastic. So thank you so much, Seren.
Preparing a new budget every second day.
Yeah, pretty much. I also want to do a huge a shout out to Emma and Chi, who are our broadcasting and community chairs, who have worked tirelessly over the last few days. Emma has spent a significant amount of her time up in the AV box, and we also want to thank all the AV crew too for all the help in making things run seamlessly over the last couple of days. But thank you so much, Emma and Chi, for getting everything working. Also have been working our local arrangement chairs, Aviad and Oscar, incredibly hard over the last couple weeks, and in the last few days they've done a lot of manual labor too, bringing different monitors back and forth, boxes and everything, and going out and running errands for us. So thank you so much, Aviad and Oscar as well. With that, we also want to thank all of the volunteers that have helped out over the days, giving you guys lunch tickets, putting up the numbers for the posters, organizing our women's event and our photography competition. So thank you to all of our volunteers. We also want to do a big thanks to all of our sponsors. Putting on a conference, as we've learned, it costs a lot of money. And we really wanted to keep prices low, especially for the students and postdocs, so that you could all come together. And so it's been awesome to have the support that we've gotten so that we can come here and have a nice conference where we can bring more students here, and we hope to be able to continue doing that in the future. So thank you to all our sponsors. But I want to give a specific shout out to the NSF who gave us $10,000 for funding of student travel fellowships here, so that we could fund 12 different students who either weren't going to be able to come, or they didn't have enough funds to come for the entire time. And so thank you so much to NSF for doing that. It really means a lot, and it grows our community out past our it's a tight-knit community, but we would like to grow as well, and so this allows us to do that. So thank you so much to NSF. And with that, we did announce the best paper on the first day, but at that time, for logistical issues and shipping issues, we didn't have our prize at that time. So we'd like to bring the best paper up again so that we can give them their well-deserved prize, which is an NVIDIA GPU. So here you go.
Thank you.
Enjoy. And with that,
And so now we have the People's Choice Awards, voted by you all. We have two categories, the Best Poster and Best Demo. So they're selected by popular vote among the attendees. And just obviously the posters or demos by us were excluded. This year we had 74 votes out of the 219 registered attendees. So People's Choice for the best poster was, thank you, Transparent Camera.
if you're here, come on up.
Yeah.
Yeah, come on up.
Good, John Wang,
We have prizes.
Zhang Haosan, De Jiachu. Okay. So
Thank you very much.
congratulations. Yes.
Thank you. Okay.
Wait, we'll take a picture a second. You got a prize, a Polaroid camera.
Okay.
So it's not transparent, but.
Thank you.
Sure, we can And our second People's Choice Award was for the best demo. Drum roll again. Winner. The modulo camera on a focal plane sensor processor.
If you're here, come on up.
Hallie So, Julian Martel, Piotr Dudek, and Gordon Wetstein.
Well, we'll get them.
Yeah, we will tell them. So, okay.
All right. So the next thing we want to announce is the results of the photography competition, and for that we have Mark Sinin, who is the organizer, to present the winners.
Okay, we came to the moment of truth. In just 2 slides, we'll see who won the best photo competition. We had 44 submissions, and we had some drama. The leading photo was changing position, but we have a result. So we'll start with the best photo honorable mention. Oh, this is our nice gallery for the photos, and they're all available online. So again, the best photo honorable mention goes to photo number 44 by William Kroska. William, if you're here, please stand up. Is William here? He is not. Okay. I see. William captured where we all wanted to be on the hot afternoons outside. Okay, and the best photo of 2022 goes to Mel White, who took the theme literally.
You should hand over the award.
Thank you so much.
So take a photo. All right. So we've reopened the submissions for photographs on the competition website. This time you can submit your photos not to compete, but to allow us to put together a nice gallery for ICCP 2022. So we hope to have a lot of photos to feature, and we'll put them all up on the website after the end of the event. All right, so before we close, I wanted to highlight one more aspect of the conference. So as we mentioned at the start, thanks to the efforts of Chi and Emma and all of the staff here at Caltech, the entire conference is recorded and it's available online at the ICCP YouTube channel. And in fact, if you go there, you'll see that it's not just ICCP 2022, but there are also all video content from ICCP from the past few years. So there is 2021, 2020, 2019, 2018, and even a very old one, there is 2011. So you can go there and see some legendary videos, like Ramesh Raskar introducing transient imaging back in 2011, and two of our recent program chairs, Bill and Yoav Sekner, looking the same as they do now and asking questions to Ramesh about his impressive work. So if you're feeling like you need something to watch and you don't feel like watching the new Game of Thrones prequel that's coming up, you can binge a few years of ICCP on the YouTube channel. So I encourage you all to go there and subscribe. And even if you don't care to watch anything, you should still subscribe for the following reason. If you go on ICCP on YouTube right now, and you Google ICCP, you will see that the first result has absolutely nothing to do with computational photography. So the more you subscribe, the higher we push the channel, and the more visibility we get to ICCP and all of the amazing work is presented here. All right? So go there, subscribe, and enjoy several years worth of ICCP. All right. So the last thing we have is a message from the chairs for ICCP 2023. We have Matthew O'Toole here, and we have Mohit Gupta presenting, doing a small presentation through video. Matthew, you want to take it?
Hi, everyone. My name is Mohit Gupta. I am at the University of Wisconsin-Madison. Over the years, I've been extremely proud to be a part of the ICCP community. And I would like to thank Yanis, Katie, Lei, and Bill, and everyone on the team this year for continuing the ICCP tradition at Caltech in Pasadena. For next year, we will move eastwards from the Pacific to the Great Lakes into the wonderful city of Madison. Please mark your calendars. We hope to see you all there from July 28th to 30th at the Monona Terrace Convention Center. It's a wonderful venue with great lake views. We will have more information soon on the conference website. Please stay tuned. Meanwhile, please reach out to us if you have any questions. Once again, thank you all very much. Safe travels, and see you next year in Madison. Thank you.
Thanks, Mohit. So I just wanted to say how high the bar was set this year. It's a little bit intimidating to take things on next year, and I just wanted to thank once again Bill, Katie, Yanis, and Lei for the amazing 3 days that we spent here and seeing all the amazing talks over the past 3 days. So, thank you.
All right, to close, we can leave our amazing group photo up. So thank you everyone for coming to Pasadena. I hope you enjoyed ICCP 2022 as much as we did, and hopefully we'll see you all again next year in Madison. And that's it.
Success. Yeah. So I really wanted to reiterate what he said.